Line segments. In the immediate future, I'm not sure how soon, but in the immediate future, I'm going to get you a thing full of graph paper, preferably a binder. The reason for that is because, I don't know, I think it would be good for you guys to do what I kind of do, and you guys can't see this, and mess around with your math. So, like, as you see, this is my binder. We had a lesson of 75 times 52 and different ways to mess with it. This is me messing around with it at home. Finding patterns and primes, getting ready to teach you guys something about that eventually. This is not you guys. Talking about division, which we're going to talk about later. You know, all kinds of stuff. I've got, I think if you look in here, ooh, this is an interesting problem. That's a sandwich problem. I don't know if you saw that up on Google Classroom. 21 minus 7, right from the other day. Something I was playing with and thinking about different ways. So, I think it'd be good for you guys to play around with this type of stuff, and if you want to do your work for your portfolio in there, that'd be super dope, because then we can just look at that and see what you're working on, and I can give you pointers one way or the other. Because I think oftentimes your work that goes into the portfolio, you're not going to want to like take a picture of a bunch of, you know, nonsense like I just had there, and be like, here's what I worked on. As you can see, right, you know, then you got to talk about it. It might be better to just have it in here, ready to go. That way, if I need to take a look at what you're working on, maybe where you might have made a mistake or where you might need some guidance, right, we can just check in here. I think that'd be a good idea. It's gonna be a different idea of a math notebook. When I say math notebook, you guys think like, wait, where is it? I've got the sound. I have the sound. I have the sound.
Write that down. Write that
oh wait,
down.
no, I don't have my speakers on.
Write that down. Write that down.
Right, that's probably what you think. What's up, Zach? You're early. So I'd like to avoid that and change the math notebook back into what it originally was. A notebook where you just write stuff down and play with numbers. How Isaac Newton did it. Anyway, he's pretty smart. So today, I want to take a look at this problem, because I posted some on Google Classroom. As you can see, let me zoom out again. Actually, double posted this one. Got a bunch of interesting questions on here. You know, your basic, how would you do it for this thing, right? Look at this problem. It says 3 concentric circles form a loop. Sorry, with spokes. Is it always possible to walk through a loop that visits each and every region exactly once? So if you look very closely, you've got this concentric circle design here, right? And they show that there is a path that you can go through that'll make sure you only walk through each section once. The question is, this is always true? Found that as an interesting problem. Again, you don't have to do any of these, just things that you might want to do. We've got another similar loop path going on here. First of all, what is the puzzle? They give you 2 examples of correct solutions. And second of all, how do you complete the rest of these down here? What do you think the puzzle is? Okay. What else do you think the rules are? Any other rules? What else do you notice about their solutions? Oh, come on. Are their solutions disconnected or connected? Yeah, they're connected, right? They got a loop kind of thing going on here. So this one they put an X by. What do you think that means? No good, meaning what? Not possible, huh? You think that's accurate? Can you guys think of a way to finish that one? Using your rules, has to be a loop, has to go through all the squares. Yeah, you could do that. So I think the issue here, if I were to look at it, is that with this one, it looks like whenever I'm in a square, I always have multiple options. You know what I'm saying? Way out is a way in. Actually, yeah, that might be. There's always a way out and a way in. Sometimes it's multiple options, right? Here, is there a way out and a way in for this one? No, so you can only go in it, you can only go out it. Probably. A lot less interesting. You have trivial. Yeah, that one can't possibly. It would be fine if we didn't have to have a loop, like, right? There might be a way to do that then. Still might not. But since I have to loop it back together, I have to go in and out from every square. In fact, we don't even need the loops. We could just do like little dash marks on, like do something like this. Let me pop this over so you can see what I'm doing. So here's our little box, right? And one of the possible ones would be this, according to my theory, right? Because there's always a way out, way in. We wouldn't really need to even draw the loop. We could just do this. Look, in, out, out, out. Boom. As long as there's at least 2 dash marks in every box, we know it's fine, right? Because you can connect them however you want. The only key difference is that this one has 4 different spots you can go from. So pick your poison. You can have this one right here, this one right here, this one right here, or this one right here. Pick any 2 of those, right? And that's your puzzle solution. I don't know. Good job, class. Sorry, I got excited. Let's pop back over, take a look. We got some more complicated ones. Obviously, the 3x3 isn't too crazy. Then we also have like this thing. I haven't really looked at this one. Because a Latin square is an n by n grid, so it can be however big you want it to be. Arrange 1 symbol per row and per column. So we got 1 symbol per row and per column. Okay. No symbol repeated in a column. So if you notice, looking in columns up and down, none of the symbols are repeated. Prove it is for sure possible to complete the picture to make a full Latin square. So playing around with that, trying to make it so none of the pictures repeat in the column. How many different pictures do we have here? We've got a triangle, a square, circle, arrow, a letter, a star, a hexagon. Is that everything? We got 7 different things to play with. This is a 1, 2, 3, 4, 5, 6 by 6. I don't know. Seems plausible, right? If we only had like 3 symbols, would we be able to do it? Why not? Yeah, right? You'd have 3 different symbols here, and then you'd be like, okay, well, what am I going to put there? Right? I ran out. So 7 with a 6 by 6? Okay, maybe. I don't know. Maybe it's not. Maybe you need 8 symbols. Now, does it matter how they arranged it down here? Like, if they had switched this column with this column, or like did something different, why doesn't it matter, Afton? Right, exactly, right. They, you know, eventually you're probably gonna have to use this right here, right? And if you don't, well, then you did and you didn't have to. Congratulations, you found another way to solve the problem. You see what I'm saying? Right, like, how they arranged it down here doesn't matter so much as long as it's valid to start with, right? And then going from there, right, you know, it'll play out how it plays out. So already we have something that should work, seems plausible. The problem's going to come up here. I don't know, something to think about. We've got 1, 2, 3, 4, 5. Ooh, it's 6 by 7. It's not 6 by 6. We're going to have 7 different rows here, or columns. I don't know, something to think about. But I want to look at this today. Some people have been like, hey, when are we getting to the geometry? Like, okay, nerds. Fine. Fine. You want shapes? We got shapes. No. No? No. Okay. Look at the first problem, the problem on the far left. The red length A to B is 7 centimeters. Oh, fun. What is the perimeter of the square? Okay, first of all, what's a square? What do we know about this problem? What do you know? Yeah. A rectangle. Ooh, what is a rectangle? A long square. Okay. I haven't learned anything yet, other than that a square is a rectangle, but I don't know what a rectangle is. Long square. circular logic here. In order to know what a rectangle is, you must know what a square is. In order to know what a square is, you must know what a rectangle is. This is, as we say, problematic. What else you got for me? Break the cycle. Not even on all sides. What do you mean? Are you talking about like the side length? Okay, so for a rectangle or a square? What are we talking about? Ooh, gotcha. Okay, so somebody remembers from way back when you had shapes class. When's the last time you talked about shapes? Been a while, hasn't it? Oh wow, complex. Circles are weird. Did you know there's actually no real good formula for the area or circumference of a circle? Ah, yes, but what is pi? Uh-huh. You see how it's not nice? It goes on forever? It's because there is no exact formula. It's an approximation. Although if we had like literal pi, like on forever always, it would be perfect. And it turns out when you take that circle and you like stretch it to make like an oval, we call that an ellipse in math world. That finding the perimeter like around that, there's no good way of doing it. Like no good way. It depends on which one you're looking at it. There's no like, oh, to find a perimeter of an ellipse, you just use this formula, like there is for a circle or like there is for a triangle or whatever. It really depends. You have to look at a lot of different things and be like, okay, for this particular ellipse, here's how you do it. And it's like this crazy, ridiculous number stuff, which makes sense, right? Because think about it, pi is crazy ridiculous. It goes on forever. There's no real way to write it. You can add a bunch of fractions onto infinity, right? 3 plus 0.1 1 over 10 plus 4 over 100 plus on and on and on and on, right? Now imagine when that constant pi changes because the shape changes, right? Now it's like, okay, we have to invent a new pi for this particular shape, right? Bizarre. Like we haven't even gotten to like, you know, Newton stuff, Einstein stuff. Already we're just like, hey, imagine a circle but not really perfect. Figure that out. And we're just like, I don't know. I could do it, but it would not be pretty. Anyway, let's talk about squares. So rectangle, different side lengths, right? Okay, I'll take that. What we're doing right now is conjecturing. I'm not saying whether you're true or false. I'm just saying, sure, that makes sense to me. If anybody would like to object, you must. Square. What's the difference between square and a rectangle? Yeah. Sure, right. That's the key difference, right? Squares all the way around. Very boring, all the same. That's actually a pretty good one, right? On camera. Rectangle, not so much, right? It's oblong. You've ever been called oblong? I would hope not. Very rude statement. Wider than you are tall, or taller than you are wide. Lots of names for that. Squares are not. So, this to this is 7. Now, these little tick marks right here are dividing up the sides into thirds, aren't they? Third of a piece, third of a piece, third of a piece. So if this much is 7, how are we going to figure out the rest of it? How would you do it? How would you solve a problem like Maria? If you want to get out some paper, I've got some. Play around with it a little bit. Oh no! Did they take my paper? Here, I'll give you some of mine. I'll play around with it. Maybe you don't need paper, right? How would you solve a problem like Maria? People at home, you're more than welcome to play along. Check my email real quick. I was feeling some buzzes. Alright, so nobody from class. How would you solve a problem like Maria? Everybody will see that more or less. Right, they're telling you that the red part right here is 7. What's the whole perimeter? Remember, perimeter is just a fancy word for fence going around something, right? The outside length. How would you solve a problem like Maria? Yeah, go ahead, Afton. Ooh, estimation. I like it. Keep going. Okay, so it looks like, how many pieces is A to B? How many like little segment things? 4, right? 4 of these guys. So you're saying if I flip it around 1, 2, 3, 4, that'd be another 7, or maybe here is what you're talking about?
Either way.
Right, yeah. We take that L and we rotate it down here. So how long does this have to be from B to this little tick mark? Right, we take that L and we put it over here. That tells us how long this is, right? How long is that from here to here? From B all the way down to there. Let me see if you can see my mouse. Oh, you can't see my mouse. So this is how much? 4 pieces? And how long are those 4 pieces? Explain that. Why did you say 7? Why do you think from B to here?
It says.
You'll see.
And
Yeah. It's 4 pieces. You see what I'm saying? It's 4 pieces. So we know that this is 7, and this is 7 up to here. So Afton's saying that 4 pieces gives us 7 centimeters. How do we find the rest of it? Come on, you guys are stumped on this earlier. I think you're starting to see it now. How do we find the rest of it? Let me pop this down so we can see it a little bit better. So here's our thing, right? We got this square. Oh, that's a beautiful square. What's wrong with this one? It's a long square. Something like this. Okay, there's our beautiful square. And we know from here to here is 7, right? 4 pieces gets us 7 centimeters. And you're saying, Afton, that look, that L is the same as this L. Right? Because it's 4 pieces long. So that's 7. What? Okay, so if we can take the L and bend it, right? Instead of bending it after 3 pieces, bend it to make a little 1, right? 1, 2, 3, and then bend. Instead of doing that, which is what we're doing here, right? He's saying, what if I did 1, 2, and then bend? Because that would be this guy, right? Can you do that? Why? It's the problem, and that's what we want. We can do what we want. Okay, great. We can do what we want, but I'm asking, why would you justify to me if I said I'm going to do what I want? I'm going to say, sorry, I'm all tangled up. I'm going to say that I can't do that. I'm going to say you can't. What would you say to me? Convince me.
It's the same length, so why you can't?
How do you know it's the same length?
Because it's the section, which is.
So what you're telling me is that the individual sections make up the whole, right? And it doesn't matter what order you put those in? Okay, I can take that. Ladies and gentlemen, what we are talking about is called the segment addition postulate. Whoa. Segment. When I say segment, you know what I'm talking about, right? A piece of something, right? These are what kind of segments? Line segments. Know what I'm talking about? Yeah? Take a line, divide it up into tiny little pieces. Those are segments, right? Segments of a line. Is this blowing anybody's mind? Do I need to slow down? Take a line and you cut it into pieces, and those pieces are called segments. Postulate. Sounds like posterior. Yikes. We're getting explicit. Postulate does not mean posterior. It does not mean your butt. What it does mean is that it's something that we would like to prove, And it's so obvious, like, yeah, man, they're the same. Like, oh my God, why are we wasting time on this? Boring. But if it weren't true, it would break all of math. But we can't prove it. What's amazing, ladies and gentlemen, is that you think of math as this science, this thing that is truth and not truth. And it's very simple. 2 plus 5 equals 7, yes or no? That's it, right? Here's the thing. There is a theorem. A theorem means something that's proven, right? That's different than a postulate. That's something we can literally prove. There is a theorem that says you cannot prove everything. Like all the things we've done in math, we can't prove it all. Some of it you have to take a leap of faith on.
Something that's proving.
I know! Isn't that bizarre? It's true. We know for sure that you can't prove everything. It's really complicated. We'll get into it someday. But at some point, you have to take a leap of faith. Isn't that bizarre in math? We call those leaps of faith postulates. We try to limit the leaps of faith, right, as much as possible. Some postulates were later proven to be theorems. Okay, we can prove that, right? But all geometry, which is just like a rule for math, right? That's all geometry means. It doesn't mean shape class necessarily, okay? We're going to talk about shapes in here. But rules for math, okay? The thing we're going to build math upon, the foundation, are postulates. They're leaps of faith. So sometimes you realize you can prove them later. And it's like, okay, that wasn't really a postulate. But this one's lasted, I don't know, since the time of the Greeks. We can't prove it. We just know it has to be, because if it didn't, man, how would we even make sense of the world? Talking to my mother the other night, and she's talking about, I can't trust these politicians. I can't trust them. Can't trust them. They're all crooks. They're all crooks. And it's like, yeah. And it's like, we're talking about one particular thing, and she's like, well, but they're all liars, so how do we know? And it's like, well, I guess you're right. We can't really prove it. But you can choose to live in a world where you assume everybody's lying, and you do nothing because of it, because, we can't tell one way or the other. Sun's shining outside. Oh, I can't trust that. Can't trust that. I don't know what to wear. I guess I'll just stay inside. Right? You can do that, and that's totally valid, because just because the sun's shining outside doesn't mean it's warm. Look outside. Sun's shining. Is it warm today? No! It's fall weather. It's sweater weather. We're the Uggs. We're the Uggs. You don't like Uggs? Do Uggs? That's not in anymore? What's in now? What's the fall look? Brown in for fall? No? Blades? You don't know? Okay, someone find that out for me. I need to know. I gotta prepare. Dark jeans, Uggs, brown sweater, hat maybe? What are you wearing to go apple picking? That's what I want to know. Anyway, so you look outside, just because the sun's out doesn't mean that's gonna be warm, right? So my mom's living this life of, well, I can't do anything because, you can never tell, right? So at some point, mathematics is saying, look, you're just gonna have to go, you know what? We're just gonna accept this to be true, because if it weren't, we couldn't do anything. And it's much more interesting to be able to do something than not do something. Agreed? Here's math class. Nope, nothing's real. Everything's made up. You can't do anything, right? It's like, well, that's true, except for you can't do anything. What if it were? If. That's what Afton said, right? If you're allowed to do this, and it's the same thing, if these two are equivalent, then we can do that. An if-then statement. How do we prove the if, right? If you could do that, all right? We can't in this case. At least Euclid and every other mathematician throughout history says we can't. This postulate has stood the test of time. It's never not been true, and it's never been proven. But we base a lot of math on it. All of the foundation of math is postulates, leaps of faith. And through those postulates, assuming you can do this, right? Well, then we can do other theorems. How do you prove that you're allowed to do this? 1, 2, 3, 4, yeah. Straighten it out all the way. Well, by our postulate here, we can say that we can add them up in any order. So this is any order, it's fine, right? I can prove that. We can call it a theorem. Most people don't. They just say, look, that's just a corollary. It's something that you just get for free. So we have postulate, we have theorem, we have conjecture, and we have corollary. Words are hard. I don't know if that's spelled right. There might be one R. I'm conjecturing that it's spelled with 2 R's. See how I did that? See how I did that? A conjecture is like a hypothesis in science, right? It's an educated guess. Here's what I think's happening, and here's why. Here's this pattern. Do I know that that pattern always works? No, I don't have it proven. But it seems to work that way. That's conjecture. A theorem, it's proven. We built it upon postulates or other theorems. Right? Pythagorean theorem, that's a fact. Assuming a segment addition postulate's true, right? You know, we always have to assume. You know what assuming does, right? My English teacher did this. We were in speech class. You know what assume does, right? It makes a out of and. I'll say that again. Assume. It makes a out of and. It makes a out of and. But that's what we are. We're mathematicians. We are these. We have to be, right? First of all, I think your education kind of sucks to begin with. We're not really damaging what's already broke, right? Your toaster's broke. It's like, don't take that apart. You'll break it, right? And then we're still where we are. But I don't think you should let fear hold you back. Take that leap of faith. Take that leap of faith. We might be wrong, but man, we can create a lot of cool stuff in the meantime. Postulate, leap of faith. Theorem, something that's proven, usually built on other theorems, or fundamentally postulates. No yawning in math class. Conjecture. Hypothesis. Corollary, something you get for free because it's already been proven, right? This is news. Okay, cool. That's segment addition postulate. That's not new news, okay? Corollary. So how long is this square all the way around? If segment addition postulate is true, what's the perimeter? 12. Why 12?
Oh.
Oh, I love this. I love this. It's 12 segments in length. And if those segments were each one, it would be 12, right? But those segments aren't each one. How long is each individual segment? That's the next question, I think, right? Well, I know 4 segments is 7. That makes sense, doesn't it?
Not a very good, yeah.
7 divided by 4. What is that about? Think about it. 8 divided by 4 would be what? A little less than 2, right? So 1 point something. Well, like, who cares? Do you see how this goes on forever? Not a nice number, like you said. When someone asks you what's 7 divided by 4, you know what the answer is? The easiest, most exact answer. No rounding needed. 7 divided by 4 is 7 quarters. Guys. Fractions, those things you hate, all they are is the easy answer to a division problem. That's it. You don't have to think about it. What's 7 divided by 4? Oh, it looks like it's 1 3/4. No. It is 1.75. No. Let me get my calculator. No. What's 7 divided by 4? 7 over 4. That's it. They didn't teach you that in 5th grade? That's it. That's it. And it's exact because it's literally 7 quarters. It's perfect. Now you might know, okay, well, it doesn't go on forever. It's 1.75. Okay, great. Fantastic. You had to think a lot more than I did to get the same answer. Here's 7 over 4. Guys, what's 99 divided by 5? Yeah, 99 over 5. What's 100 divided by 5? 100 split 20, right? We can simplify that, right? 20 is a little bit easier to understand than 100 right? That's why we call it simplification. Not simplification if it's not simpler. And sometimes we make you simplify the problem and it actually makes it more complex. Simplification is subjective. It means you get to choose what's simpler and what isn't. Okay, so we have segment addition postulate. That's interesting. That came up very quickly. That law of geometry, very simple problem, came up very quick. Wouldn't postulates be the same thing as taking an assumption and then try to prove something later? Yeah, it is. It's if this is true, this is true. We're not going to talk about the first thing. We're just going to assume that's true, right? Like, if the sun is out, then, or how about this? How about this? The most famous postulate of all time. You ever heard of René Descartes? The Frenchman, Renaissance man. He was a scientist, painter, all kinds of stuff. He invented the coordinate plane, that little graph thing over there. You love him, you hate him. He said the famous philosophical sentence, "I think, therefore I am." And why was that significant? Because he's saying, look, postulate, do I exist or do I not? Ain't nobody got time for that. I think, therefore I am. I exist. We're just going to say that's good enough. Thank God, right? Way too much time worrying about do I exist or not. Is this the Matrix? Have you seen the Matrix? Take the red pill. Okay. You ready? You want to do another question? You want to do another one? Sure you do. First one was a free taste. Now I got you hooked. Y'all got any more of them problems? All right. The red length, A to B, is 18 centimeters. What's the perimeter of the rectangle? Ooh, rectangle! That's what you said. Rectum, I barely know him. All right, so this length is 18, they're telling us. Fantastic, wonderful. Ooh, great question. Anybody have a conjecture about that? Anybody have a thought? Difference between a rectangle and a square here? How do we know this one's a rectangle? Go! Sure, right, it's oblong, right? It's not the same on every side. Now, how do we know this one's different? They don't give us any measurements, but they do give us tick marks, right? They say this is 2 segments, that's 3 segments. Another postulate, 3 is always bigger than 2. Always. As long as it's like, 3 apples and 2 apples. If we're like 3 apples versus 2 dump trucks, well, But we're talking segments here. 3 segments, 2 segments. Now, if the segments are all the same length, then that changes the problem a lot, right? But we're going to assume, and you know what that does to us? It makes and that all the segments are the same length. So if these guys, this is 18, how are we going to find the perimeter of the rest of it? How many segments we have right here inside this red line? Can I zoom more? I can zoom. How many segments we got there inside the red line? 4, right? 1, and then how do you know there's 3 down here? It's not really marked. Aha! So something else about rectangles. They don't sit like this, do they? Slanted. Right? The top part is immediately above the bottom part. Where things are positioned in space, we call that angles. So there's a 90-degree angle here. You guys remember Grandpa SquarePants? Right? Rock bottom. Grandpa SquarePants always said never chase after a bus. Especially one that's going up at a 90-degree angle. Right? No? Okay. Need y'all to go home and watch SpongeBob for homework. I said we wouldn't have any homework, but you have to watch it. Go watch Rock Bottom. I can't... Actually, I've got this one. Hold on.
I can't understand your accent.
You know what I'm talking about, that episode? Carly, did you not get to watch SpongeBob as a child? Okay. I'm gonna say that explains a lot.
Where can people watch it?
Oh, just Google it.
No. I mean, like, where's good streaming platform?
Amazon Prime, you can get season 1 through season 3 for free, which are the only seasons that matter. But you just Google it. Yes, cartoon. Yes, cartoon. Okay. But you didn't hear that from me. So this is 18, and there's 4 segments there. So you want to figure out how long each segment is, or you want to try to be clever and not figure out how long each segment is? If this is an L of 4, right? 4 segments get you 18. Well, can't we do another L up here? So the 2 L's put together, how long are they? 10 plus 10 plus 16. 36. Now what about these 2? How are we going to do that? What are you thinking, Brennan? Did I interrupt your thinking? I'm sorry. Let me pop this on down. Should we put this up on the back wall? Do you think it's pretty? Here. Put it up on the back wall. There should be tape back there. If there isn't tape, let me throw some at you. Anywhere you want. Continuation. Yeah, the time is meaningless in coronavirus. Does anybody really know what time it is? I want you to look at that problem. I want you to do that. Play around with it. See if you can figure it out. Find a clever way to solve it. I'll see you later. Bye. My dad forbid my siblings from watching SpongeBob because he found that it was too inappropriate. I love the word inappropriate. Inappropriate to what? Like, if I'm going to a Met Gala, right, it might be inappropriate to show up in shorts. Oh my God, right here, right now?
Yeah, too.
Okay, please don't do it in my classroom. Not on the circle rug, not on the circle rug! Does anybody really know what time it is? Does anybody really care?
Nope.
Love how that song asks the obvious question. Hello, Katie! Alright, so everybody was here, but Macy wasn't, and Parker wasn't, and I didn't see Chase. Not sure what's going on with that. Or Paul, or Grant, or Geraldine. Where? Internet down? Guys, did you have a lot of people that were online absent today?
Me?
Yeah, because my first hour, I'm missing like everybody.
I don't know.
Okay. So Macy. Oh, I did not. I'm sorry. I didn't mean to not. I'm looking around trying to. Okay. Yeah, you should be. Do a full meeting with me. Easiest class ever. But there's good news. Grades are due Tuesday. Today's Monday. Hello. I missed you. Yeah, it's just not in here, please. You can have it. You want it. Okay, well, you might want it. Oh, you know, writing down ideas. Math stuff. Just think about math stuff. Wow. Okay. I see how it is. I see how it is.
What kind of shirt matter?
We got evicted. I'm trying to avoid that myself.
I could get you one of these shirts.
No, I'm good. I don't have money. That's the whole point. All right. All right, kiddos. I'm going to direct your attention to the board. Does anybody really know what time it is? Post some new stuff on Google Classroom for you. I'll show that in a little bit. Take a gander up there. If you're here, let me know. First hour might have had video problems. I'm not sure. Although they should have emailed me if that was the case. I got one email from Miss Sandra. Okay. Y'all have a good weekend? Well, it's over now. Sorry. Hi. How'd it go?
Great.
Oh, wonderful. Sarah's here, Haley's here, Jace is here. Awesome, we'll do Tendy and then we'll get on it. Alrighty. Missing Ethan and Nathaniel and Jaden. Okay, Ethan's here, awesome. And it looks like everybody else is here. Shion's here, right? Yep. Okay, awesome. We even got Corinne. He's just in the bathroom. Jaden's here. Awesome. Hey, Jaden. Jaden, we got to get together and do a portfolio review, bud. So that's the only grade, and we got grades due Tuesday, fortunately. Just send me an email with what time we can meet. Anytime after school, like 1:05 to 3:25, something like that. Let me know, man. Alrighty, so I want to direct your attention to Google Classroom. So what I'm going to do is I'm going to pop over here. So you'll see I posted some stuff last night and the night before, some other interesting questions that you're more than welcome to go check out for your portfolio. By the way, portfolio reviews. The ones that did it, useful, right? We agree now? Yes or no? Yeah. I felt like it was pretty good. The plan from now on, if I haven't said it already, is that we're going to do every other week A-Day, B-Day. So Wednesdays, A-Day people will go, then the Wednesday after that, B-Day people will go for their portfolio review. It'll give us more time to get that done. More time to talk. I felt like the more time we had to talk, the better they went. I got those recorded, and for most of you, I think it's just my algebra class. They're always in the back burner. For everybody in geometry that did a portfolio review, I should have a grade in for you. And also the link to the video, because Google Classroom, it was more of a pain to edit the audio than it was the video. So I just did the video. I have the video of our conference. So if your parents want to check that out and be like, why'd my kid get an A? I don't believe it. Then go see that and be like, oh, okay. Yeah, so that's the thing on that. I got some problems for you that you can look at. 89 times 76, like how would you go about it? What's the most clever way you can think of to go about that? We've got some questions like this. Here's some concentric circles. Is it always possible to walk through each path only once by making a loop somehow? And they give you different ways of doing it. So we have 3 concentric circles, right? With one line drawn through them. 3 concentric circles with divided into thirds, right? Then we have to divide into fourths, then into fifths, etc., etc. You can see the pattern. Is it always possible? There's a question. We got another one. Speaking of paths. First of all, the question is, what is the question? What do you think? And this puzzle, they give you 2 possible solutions and an X. E doesn't work. What do you think the question is? Yeah. No, give it a shot. Gotcha. So what we had here was a conjecture. Word of the day. Conjecture is something that I thought, because I thought I saw a pattern, right? And then maybe that pattern breaks later or not. I don't know, right? What she did right there was a beautiful example of this, right? You had a counterexample second, because your conjecture was, oh, we got to go around the square, right? The square that's shaded in. And then immediately, oh, counterexample, not quite, right? Corinne. Nice shoes, Corinne. Look at those shoes. Do they make you run faster? Oh, I got flames on my car, baby. Ooh, yeah. You're trying to make a loop or something, it looks like. And again, maybe that's not the real question, but who's to say? We have no counterexample, right? How do we make a loop that goes through every single square? Okay, that makes sense. That makes sense, and doesn't go through the purple one, right? So let's look at this one, the X. I'm assuming that means it can't work. Is there a way, if Corinne's question is correct, there should not be a way to make a loop that goes through every single square. Now, how would you prove something like that? My first hour, realize this, and it's very clever. Hard problem. Let's think of an easier one. Think of an easier one. Let me show you on here what they did. They said, okay, here's the problem, right? And the shaded one was up here, I believe, right? Okay. So, making a loop. If I were to start here, I have options. I can either go up, right, or down. What happens if I go up? I reach a dead end, don't I? So I don't want to go up. Now think about that dead end. Why is it a dead end? I was able to go in, but what wasn't I able to do? I was able to go in, but what wasn't I able to do? Go out. So my first hour conjectured.
But wouldn't it have...
Ooh, exactly. It's almost time to restart. That's not good. Wait, what? Wait an hour? Okay, great, fantastic. Sorry, that's not good. You didn't see that. Windows 10 is about to restart. Okay, so we're gonna make the best of this. Yeah, so Corinne said, wouldn't you have to go out in order to make a loop? You have to be able to go in and out, right? That makes sense. So really our problem is not making a loop necessarily, it's can we go in and out of every square? Can we go out and in the square? No, so not possible. Can't be. There's no way to go into that square by also going out. Now, if we could just do like, I don't know, something like this, right? Where it like doesn't have to connect back on itself. Maybe it's possible. Turns out it's probably not. I had to cheat. So let's look at the ones that were correct. They had a space here, right? Can we go in and out of every square? Well, this one, can I go in and out? Yep, here's an in, here's an out. Pick your one, right? I don't even need to draw a loop. Eventually, you're gonna have to go through those sides, right? You can either go in then out or out then in. Here, can I go in and out? Yeah. What about this one? Ooh, I got lots of options. Okay, let's say we go here. There's a loop. Now, you might have noticed we had options, right? We could take this one from the middle. We could take this one from the middle. We can take this one from the middle. We can take this one from the middle. So, same color. Yeah, that's pretty close. Let's do yellow. Yeah, that's so similar to the orange. Let's do dark orange. Actually, let's do green. This is important. This matters. So every path that you would create with this guy is going to be the same for all the squares except the middle. The middle's the one you choose with, right? It has actual options. I thought that was pretty clever. Bryn, nice job.
Thank you.
Nice job, Mika. Makes a hard problem a lot easier. Can I go in and out of every square? So why did this problem ask, or as a teacher, thinking as a teacher, right? Why did this problem start without a question? The first question being, what's the question? Because just because they ask a certain question doesn't mean that's the best way to ask it. Right? Corinne did a great job of saying, how do we make a loop or whatever, right? Going through everything. And that's true. But there's a much easier question embedded in that. Can I go in and out of every square? It becomes boring at that point, right? Marissa's like, yep. Exactly. How long have you been growing this out? You did?
Yeah.
Oh, girl, hate when that happens. It's fall season, guys. I'm not seeing any Uggs or Uggs out. What's in now? Right? Dark jeans, brown, little hat to go apple picking with. Like, what's the look? These? Flaming hot shoes. Gotta go fast. That's what fall is. Gotta go fast. Coach, I gotta wear my shoes. They're not regulation. Doesn't matter. Catch me if you can. You'll never stop me. There you go. What about this problem? Oh no, you can't see it. You can't see it. You can't see it. Let me zoom. How do you solve a problem like Maria? Look at the first one. Relax. Why'd you say, oh no? Oh my. Oh. Oh my. We just zoom in on the one. Here. Oh, I can't. Here, I'll draw it. That's part of my job. We got this box type thing. Right? Something like that. Beautiful. And it's got like little things here going on. And then it's got a little red line from A to B. And it's saying that that's 7 centimeters. And it wants to know what's the distance all the way around, otherwise known as the perimeter, the perimeter. How do you solve a problem like Maria? Yeah, sure, I don't care. Yeah, of course, everything's available. Anything we do in class and anything you do that is math related can go in the portfolio. We're getting out the calculator, good idea. Campbell, tell us what you find. Oh, sorry. That was awkward. How would you solve a problem like Maria? Katie's like, oh no. Wait, Katie has something to say. She raised her hand, Corinne. Calm down. Katie. Isn't it 21? Okay, take your time. Oh, there's another one. And another one. Okay, so we have another L, which means this is 7. Okay. Okay. Okay, so here is what Katie is conjecturing. She is saying that, look, an L always equals another L. And again, what are we talking here? We're talking L of this length, right? Always equals another L, even if it's a different color, and even if it's going a different direction. Right? Any way you rotate it, it's going to be the same. We call that rotational symmetry. It's the same, even if you rotate it. Make sense? I am not rotationally similar. Because if I rotate, I'm not really the same 100%. I'm kind of different, which is how most of my students describe me. But this is rotationally similar. Okay, conjecture. If we're allowed to do that, then this is 7 as well, right? Now, how do we prove the if? I don't know. How do you prove that that's the same? Just seems like it has to be, right? Okay, what about this guy? Now, wait there a minute. That's not an L. At least it's a weird looking L. L's are supposed to be misshapen, one side longer than the other. Can we call that an L? Why would you think we'd be able to? Corinne!
What?
It's your turn. Why do we think the green L is the same as these L's, even though it kind of looks different? Why would you say it is the same? Okay, there's a lot to break down there. First of all, she used one of my favorite words. My English teacher for speech used to talk to us about assumptions. Corinne, I've missed you. All right. You know what she said about it? When you assume, it makes a out of and. She said it makes a out of and. When you assume, it makes a out of and. Anybody know what I'm talking about? Makes an ass out of you and me. We're going to do that a lot in here, because that's just what mathematicians do. We're not afraid to look like this. My mom! Okay? Talked to my mom last night. I know! I have one! Can you imagine someone spawned me? Did you guys I used to be a twin. Did you know that? Another time. So, another time. Okay, we don't have time for this. Relax, okay? I was talking to my mom. Can't trust these politicians, you know, they're all liars. You just can't. They say one thing, you say that. I just don't know what to do. Just don't know what to do. Can't do anything. That's one way to live. And she's not wrong. All politicians are liars, right? We talk about this all the time. But you can live your life like that and be like, because they're liars, I can't do anything. You know, I can't trust them one way or the other, right? The sun's shining outside. Can't tell that it's warm. Can't do that. Don't know. Gotta stay inside. It's a very boring way to live. Doesn't mean she's wrong. And she's boring. You got to take a chance sometimes. Leap of faith. Make a conjecture. A conjecture is something that you think is going to be true because, look, there seems to be a pattern here. I've got an idea what's going on. Maybe I'm wrong. That's okay. I was talking to somebody else the other day. Mr. Mack, what if you're wrong about how education works? What if you're wrong? You got these kids' lives at stake. So you're risking that. That's an awful big risk. If my toaster is broken and I take it apart to fix it, and I don't fix it, the toaster's still broken, right? Who cares how broken it is? It's broken. There's nothing to lose here, right? That's how I think education is. It's already broken. Oh no, you broke education! Right? I mean, anyway, I think it's time to take chances, make mistakes, get messy. You gotta put your foot in the ground and say, this is where I'm going. Take a step forward. That's what a conjecture is. You're conjecturing that this L is the same as that L because it has to be. Now, that's terrible reasoning, right? Because it gotta be. How can it be anything else? But here's the thing. There's a theorem. Theorems are proven in mathematics, okay? Theorem. Something that's proven, like Pythagorean theorem. It's real. However, theorems are proven with other theorems. You see the problem there? What came first, the chicken or the egg, right? The chegg? Okay, that's a whole level of like evolutionary biology that I don't want to get into. The theorems are proven by other theorems. There has to be an original chicken to make the egg or something like that, right? It turns out there's a theorem, something we've proven. A theorem, something we've proven in mathematics, okay? And the theorem says not everything in math can be proven. I'm going to say that again. We have a theorem that says, proven, that not everything can be proven. In other words, at some point, you got to take a leap of faith. You have to, even mathematics. The science of math, right? No. Those leaps of faith we call postulates. The big word, sounds like posterior, but it ain't. Not this. It's a leap of faith. It has to be true because if it weren't, oh my God, right? If 4 segments put together like this are different than 4 segments put together like that, then like we're living in a world that I can't do anything in. Can't trust them. At some point, you have to say, you know what? That's probably true. It's okay if we go out and do math based on that. If I end up being wrong later, okay, whatever. Or maybe we end up proving it later and it's not a postulate, it's a theorem. Great, fantastic. But in order to do interesting things with our lives, we have to take a leap of faith and accept that, like, you know what? Maybe this is true. Same thing in math. So we're just going to say that's true because how else could it be? We're not going to accept that for a lot of things because you see the problem with that, right? If it's always just like, we'll just accept it. Well, have we ever proven anything then? No. At some point, you have to also switch over to proving things. But to begin with, you have to take a leap of faith. This is true in life as much as it is in math. Take a chance. Shoot or shoot, right? What they say. How do we know this is the same as that? Well, Corinne was talking about how 4 segments, no matter how you order them, have to be the same, right? So this is Corinne's postulate. Corinne, it's 2 R's and 2 N's or 1 N? 1 N, that's right. Now, unfortunately, someone beat Corinne to it. We don't know who. We call it the segment addition postulate. I think that's fine. I don't care, as long as we all know what we're talking about. Corinne's postulate. Segment addition postulate. This one's SAP. If you spell it out, that's fun. CP, I don't know. You're thinking outside the box here. Those aren't tick marks for that. We haven't talked about that yet. But you're right, you're right. She had my class last year. So she's like brilliant. You should have met her before we had class. So dumb, but like afterwards, look at her. Look at her now. Look at her. Her hair, the shoes. Okay? New woman, yes. Ooh, another way. Go for it. Okay. So shifting it? Got it. So one way she knows it's the same is because she can put it next to it and measure, right? Now, in imaginary math land, we don't have rulers, right? Because imagine ruler. Okay, great. You can stretch it, like, it doesn't do much. But if we know this right here is a pen and it has a certain length, how do we know that this has the same length? Well, we can put them up against each other, right? We can do that in math land too. We've got 4 segments here. That's where this comes from. Segments, pieces of a line, right? Segmented, cut in pieces, right? You smell them stepping in? Okay. We've got 4 segments. We can put those 4 segments over here. So I can take those 4 segments, this guy, this guy, this guy, and this guy, and put them over there, and look, they're the same. That's good enough. Now, it's a postulate that we're assuming all of them are the same, and you're allowed to do that, right? That you can take this apart and put it back together, and it's the same thing. But I think you'll conclude that if I were to take this pen apart and put it back together, right, it's the same before and after. Same thing with this. If we take the segment apart and replace it, it's fine. Segment addition postulate. If you take the segments and add them up, you get the original. If you take the original and pull them apart, it's still the same length. Smell what I'm stepping in? Okay, this is a postulate because there's no way to prove this, but oh my god, it has to be. Can't trust him. Oh no, can't do anything. No, eventually we have to say, okay, look, we're gonna trust that you're allowed to do that. Because think of all the good things we can do with it now. Instead of having to have a ruler that's the exact size of everything you want to measure, you could have one ruler and stack it on top of itself. How are you gonna measure this classroom? Well, you gotta have a classroom-sized ruler, right? Not very useful. I could have one ruler, just stick them up. Put them all together. Conjecture, theorem, postulate, corollary. I think it's how you spell it. Corollary, it's my conjecture, that's how you spell it. You see how I did that? I'm conjecturing that corollary is spelled like that. I don't know. Stop laughing at me. All right, so corollary. It's something you get for free. No, you're not in math class. It's something you get for free. So if this is allowed to be moved into that, do I need a whole separate statement to show that this black line is also the same length? No, right? 4 pieces, no matter how you arrange them, is still going to be 4 pieces, right? You don't need a whole separate, okay, theorem 1.1 of Corinne's postulate, right? No, it's a corollary. You get it for free. It's all kit and caboodle. So conjectures, ideas, we saw a pattern, we think this is what's going on. Maybe the pattern's going to change, I don't know, but it looks like that. Theorem, something that's proven, either by using other theorems to prove it, or a postulate, the leap of faith, the OG. Try to limit those as few as possible. Euclid's, are you finished? Not, love it, I love the honesty. I'm glad you're in my class. Euclid has 5 postulates. There's one that's in debate, actually, about whether it has to be a postulate or if we can actually prove it. Like if it's already proven by the other 4. Very interesting. Very, very crazy in the math world right now. We're all just like... But anyway, Euclid's geometry only needs 4 postulates, maybe 5. I think. Maybe it's 5 or 6. I can't remember. Numbers are hard. And then corollary is this thing you get for free, okay? When I say those words, I hope you understand what I mean. You'll get used to them. Don't try to memorize them. There's no vocab quiz. Okay? But if you don't know what I mean, just be like, wait a minute. So using segment addition postulate, we can prove that this is 21, right? Because if the red is 7 and the blue is the same thing, that means the blue is 7. And if the blue and the red and the green are the same thing, because it's all 4 segments, then the green is 7. Whole thing's 21. If segment addition postulate is true, right? If you're allowed to take something apart and then stick it over, do whatever. I don't know. Seems like a reasonable assumption. Makes a out of and. I know you guys are ready for the next one. You're so excited. You're like, y'all got any more of them problems? Anybody a Dave Chappelle fan? No? Okay. Don't know who that is. Okay. No. Corinne, I said earlier that you took my class and that you learned so much, but apparently you learned nothing. Other than have cool shoes and great hair. But honestly, you don't need great hair. Look at me. Look at this. All those shoes are pretty great. Got these. The hair's about to change? No. 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 Getting longer? Oh no. Is it staying the same? It's not. It's about to change. It's getting shorter. Haven't you learned anything from Marissa? Look at her. Look at that poor child. Do you want to go down that path? God. You need like Sarah McLachlan with the "In the arms of an angel." Please donate now. Girls every day are cutting their hair just like Marissa. They need all the help. I don't know. I'm done with this. I'm done riffing on this. Your hair looks fine. Back in character. All right. The res length from A to B is 18 centimeters. What is the perimeter of this rectangle? First of all, rectum, I barely know him. What's a rectangle? What's a square? Come on, remember shapes class. Annie. Hi. What, Corinne? Okay, go ahead, Corinne. She's just too fast, it's those shoes. Ooh, okay. Square has all 4 equal sides. But a rectangle doesn't have to have that? Go. It can. Ooh. He's right. So a square is a rectangle with all the sides the same. Well, what's a rectangle? Doesn't have to have all the sides the same. What does it have similar to a square, though? The corners. Something about the corners, right? Four sides has four sides. Very good. Notice how the top and the bottom are always directly above each other. It's like they went to the chiropractor, right? They're in alignment. They're not slanty like this. That's why we build houses like this. 90-degree angles. Oh my God, would you calm down? Okay, these kids are not ready for that. You've never heard of 90-degree angles. When she says that, you don't know what she means, and she's just confusing you. Why, I'm the teacher, and Corinne is gonna cut her hair on Tuesday. Okay, so how would you solve a problem like Maria? I'm gonna draw it. And that's how I'm gonna solve it. Okay. So there was like this, and then there was like that, and then like this. You could get with this, or you could get with that. You remember that commercial? It had like the hamsters driving around in the car. You remember. All right. And where was the thinger? Okay, it was here. And they said this was 18 centimeters. How would you solve a problem like Maria? This is easy. Boring. Then prove it. Get it? Okay, enough, Corinne. God. Take off your shoes and calm down. Let us all catch up. If this was a YouTube video when I said lettuce, you would have seen head of lettuce. And when I said all, you would have seen like the laundry detergent pop on screen. And then ketchup. Yes. Katie. You live your entire life just seeing L's everywhere. Loser, loser, loser. But on top. Katie's like, okay, I'm done. Okay. It is usually just best to say, okay, to whatever I'm saying. So you're saying, according to segment addition postulate, SAP or Corinne's postulate, that has to be the same, right? Okay, where are your gods now? Okay, Katie, yes? Hold on. What kind of toothpaste are her nails? What is that? What kind of toothpaste is that? What toothpaste is that? No, it's not Crest or Colgate. It's the other one. Someone figure that out. Katie, keep going. It is. Okay, what is it? Oh my God, this is taking forever. I got bored.
Oh my God.
I'm getting bored.
Okay, so I added 18 plus 18.
Oh, this one? I want to know about the nails.
About the nails? I didn't figure that out.
Okay, fine. Okay, go ahead, Laura Lee. You can interrupt Katie because she's okay.
I'm gonna pretend like it's there.
Okay, I'm interested.
I added
You just divided it up that way and you got 9? What does the 9 mean? The other side length? Interesting. So conjecture, this is 9. Katie, can you go ahead? Wait, hold on. Mika, do you have an answer? It's not. It's not. It's not the right shade. Who does? Who's talking? I can't tell. Like ventriloquism there. Campbell? Thank you for updating us on that. I think it is.
Yeah.
I think it is. I think it is. Your nails are aqua fresh. Katie?
It is aqua fresh.
Yes! Finally. Now we know it's true. Katie? Ooh. Division? Division? So this is half. And how do you know it's half? Because it's 2. Right? And we had 4 over here. And you know the relationship between 4 and 2. The way we show relationship in here, one of the great ways, is actually division. That's all division is. It shows a relationship between numbers. What's the relationship between 4 and 2? It's double. Right? What's the relationship between 5 and 3? Oh, it's a weird relationship. It's 5/3. Weird. You know, you have that one friend, right? Relationship's kind of weird. Like, but she's a good girl. Why is she dating that guy? And she's like, well, I'm not that good. It's like, Sarah! That's what 5/3 is like. But 4 halves? Oh, man. It's just 2. They're related by double. So the 4 is twice as big as the 2. That's what we're saying here. So the 18 is twice as big as the 9. How do we know that relationship's the same? Because another way to do it is 18 and 9. What's their relationship? Double. Say it with me now. Double. No, with me. It's like music. Ready? We breathe in like this, and then we say it like this. Double. Very good. I can make you guys do anything. Isn't that funny? Teacher's like, okay, now everybody say it. And then you guys do. What's wrong with you guys? You've been trained. It's twice as big. And you know the relationship between 18 and 9 is the same as the relationship between 4 and 2. In other words, you did this in your head. 4 over 2 is this. I'm not using colors anymore. Is the same as 18 over what? What? Yeah, you did. The relationship between 4 and 2 is the same relationship as 18 and what? 9! Yes? Thank you. Thank you. Marissa's like, today, I'm going to participate. Oh, he already said. But you stuck with it. I like it. I like it. Never give up, never surrender. So, in total, what do we got here? How would you add these numbers up? You're like, I wouldn't. Say again. Oh, that's true, yes. Marissa already answered that patiently. How would we add these numbers up? Let me re-ask the question. How would we add these numbers up? Because we gotta know the whole thing, right? The total. That's another. Is total toothpaste? Like Crest total? Yeah, okay, keep going. Not with the toothpaste. How would we add these? How would you add them up? Campbell, now's your cue. I would get out my calculator. Oh, just kidding, not doing that. Okay, other than Campbell, what would you do? Farron. How would you do that, though? Okay, and how would you do that in your head? Marissa? Did you have your hand up? Okay, that's fine. How would you add them?
Add 'em.
You know what I would do? I'd see these are all multiples of 9, right? Because I know they have a relationship. And I'd say 9 plus 9 plus 9 plus 9 plus 9. How many 9s is that? 9, 9, 9, 9, 9! 5 9s. 45, right? Another way. That's 10, that's 20, that's 20. That 50 minus 2, 48 minus 2, 46 minus 1, 45. 10 plus 18 is 28, minus 1 is 27. 27 plus 20 is 47, minus 2, 45. I don't know. See y'all later. Take a look at that next one. Take a look at this one. Take a gander at the next one. Maybe write about it in your journal. Bye. I love you, Jenny. That's how I did it, Lily. Bye. I love you all. Bye. Good thing you went beforehand. Can you imagine how awful that would have been? You never would have made it. Would have lost it. You spray it all down. Oh, dang, girl. Come on, let's go. Oh, my God. You guys had to go slap fight? Who would be better? Wouldn't there? Wouldn't there? Just come from here. I feel like that would be true.
I have to show you a picture.
Oh, I'm ready. Bye, Shion. Shion, we need to meet and get your portfolio taken care of. You have a great right now.
McAnally.
Yo.
Go to the ortho tomorrow.
Oh, exciting. Are you taking the ortho bus?
No.
Oh.
I'm gonna have to speed run my braces. This and on and off in here.
Show me.
This.
Okay, yeah. This is good, especially for your personality. And you're using color or purple or what color? Oh, the blue.
Yeah.
Dig it. Like power, man. Favorite. Do they still do the ortho bus? That was adorable. Okay, I figured Corona put an end to that, but that's funny. It was so cute. It'd be like 10 people gone from my class. What's going on? They're like, oh, they took the ortho bus. Last year, my first year. I'm like, what do you mean ortho bus? Right? Oh, all the brace kids get together on a field trip. Go get matching rubber bands. And it's like, wow, amazing. Bye, Jace. Like, oh, that's cute. I'll direct your attention to the board. Got everybody cleared in here, I think, right? Yeah, we all. Your grade should be in Skyward now, if you met with me, which is everybody. And you should have a video up, except for Geneva, who did it on Discord. My Discord thing didn't work. We're probably just going to do
Video.
the video of our conference, so what we talked about. Yeah, I was going to just have the audio, but then it was just, although it did take more time to upload it. Grades are locked in, not locked in tomorrow. Grades are due tomorrow to be sent home. Because school for something it does midterm of the quarter, right? Then it just midterm of the semester.
We changed time to next week.
Is it really? We fall back, get an hour of sleep.
Oh no, we changed school time.
Oh, we do?
Yeah. Yes, that's what.
When did that come out?
That's been up for like a week.
See, I don't know things, guys. I don't know things. I never know. I don't even know when like winter break starts. They have to tell me, okay, not going to be here tomorrow. I'm like, oh, okay, all right. All right, I'll go home. First Sunday, November. Got it. Oh, man, we're approaching November. That is wild. All right, so anyway, I posted some questions up on Google Classroom, some more problems that you might be interested in taking a look at. There's this guy right here, 0 zeros. It's kind of hard to see. It says use only these 5 numbers, 10, 100, 1,000, 10,000, 100,000, using basic operations, addition, minus, times, and divide, and brackets if you want. Change the numbers so that they all don't have zeros. So, like, do something with those numbers to make a number that doesn't have a 0 at all. Here's an interesting question. Hi, Nevaeh. Hey, Max. Hey, Steven. And I've got more on Google Classroom. Lots of interesting problems. Let's look at this guy right here. At least I think they're interesting. So basically, this guy, right? Find a clever way of doing it. How would you do it, right? We talked about that. Another thing is this guy right here. Basically, it's saying, hey, look, I have 3 concentric circles, 3 circles wrapped around each other. This one's divided in half. Can you draw a path that goes through every section only once? And it looks like for the first 3 you can, right? This is divided in half, that's divided in thirds, that's divided in fourths. Can you always do it? And how would you prove that you can? That's a tough question. Speaking of tough questions, this one doesn't even have a question. The first question is, what is the question? So here's 3 examples. What do you think's going on? I will take attendance now while you guys are thinking about that. While you're stinking about it. Do it over here. Ooh, second hour. Did I take second hours tonight? Did I not? Must not hit save. I don't see Lindsay. I see Geneva, Skylar, Maddie. I see Carter. No Josh. No Rowan. And again, if you're friends with these people, text them so they get up. I see Max. I see Cliff. I see Nevaeh. I see Adam.
Adam!
I see Steven. What do you think the question is? What are the rules? What's the problem? Ooh, don't touch the gray square. It's purple to me. Take your shirt. You wearing a gray shirt or a purple shirt? There we go. Okay, that's fine. My sister's colorblind actually, which is really rare for like women to be colorblind, but it's because she's like a weird person. She's all kind of. And when we play Twister together as kids, she would be like, right hand red. You put her hand on green, and we'd be like, no, Kayla. And then we'd say like, right hand blue, and she put her right hand on blue and be like, no, that's not the right one. We kind of contributed that. We could have helped, you know what I mean? We decided to make it worse. Can't tell her left from her right. It's great. Ruined for life. Okay. You're not allowed to touch purple. What else? What do you think this X means? Ooh, can't go out of the box. Okay. I like that. Anybody else have any other ideas? Yeah. Ooh, we gotta have a loop, right? Cool. Cliff says, I'm assuming that you have to make a shape without touching the purple square. Yeah, you gotta make a loop without touching the purple square. And what else? You just make any shape? What do you notice? All the white boxes. You gotta go through all the white boxes once, looks like, right? Can't go outside the box. What else? My other classes said this means that this one is impossible. Now, based on our rules, if our rules are the correct interpretation, right, then this should not be possible, if that's what this means. What do you think? Is this one not possible? You think so? Why do you think you can do it? Because anything's possible. I love that. I love that. You can't go diagonally, is what Lily says. Cliff, you say, while using all the squares. Yep. My first hour class, pretty brilliant about this. I'll tell you something. What do y'all know about loops? What makes something a loop? Yellow? Yeah, what makes something a loop? It connects. So if I were to start here, and I left, okay, what would I have to do next? So go up and then over. Now, what about this one? I'm going to show you something. Doesn't mean it's impossible, but it means that this way doesn't work. Let me show you. This was the other one that they had the X by, right? If I start here, what's the problem with starting here? I can't get back, right? I can either leave or I can come in, but I can't do both. My first hour made a conjecture. A conjecture is, I see a pattern, maybe this is what's going on. Maybe there's a counterexample later that breaks the pattern, right? In kindergarten, they used to be like, square, circle, what's next? And everybody would go, square. And I would go, and I'm serious. Triangle. And they thought I was dumb. And maybe I was, but my point was, maybe the pattern isn't there yet. Maybe it's square, circle, then triangle, and then it repeats. Who's to say? So my conjecture was that, right? A conjecture is an idea. You think the pattern's going to hold. So our conjecture is that in order to make a loop, you need to be able to exit and come back in. That's why this one's impossible. Because no matter what path I make, eventually I have to go through the square, right? To get all the squares. And once I go into that square, I can't get out. You see what I'm saying here? The problem is simpler than the question we asked of how do we make a path, right? Hi, Lindsay. That's a valid question, but it actually breaks down more simply. Is this one possible? Well, no matter where I start, right? I'm going to have to go in this and out this. So here's an in, here's an out, right? Or vice versa, right? No matter what path I make, I'm going to do that, aren't I? In and out, one or the other. No matter what path I make, I have to go in and out of this square. No matter what path I take, I have to go in and out of this one. Oh, I have options on this one, right? No matter what path I take, I have to go in and out. No matter what path I take, did it. Now notice we had some options, right? The middle is the only variance. So if you found a solution, the only difference will be which path you took through the middle, more or less. Right? Everything else, only 2 choices there. And you have to use both, right? One has to be an in, one has to be an out. Much easier problem. How do I know this one doesn't work? Because I can't go in and out of this square or this one. No matter where I start, what I do, I'm going to have to go through that square, and I'm not going to be able to get back out. So it's impossible. First hour. Whew. It'd be illegal to do math that early, but look at them. How would you solve these problems like Maria? Ooh, they're bigger. Uh-oh. Does that change anything? I'll let you ponder that. Today we're going to take a look at this, because somebody was like, you know what? Isn't this shapes class? We haven't learned about any shapes. We haven't talked about any shapes. And I was like, you know what? You want to talk about shapes? We'll talk about shapes, baby. I got all the shapes. We got squares, we got rectangles, we got that. We got them all. How do you solve a problem like Maria? Oh, you don't see it, do you? You don't see it. Take gander of those. Ah, we got squares, we got rectangles, rectum, I barely even know them. And we got the other one, the other shape. Those are the 3 shapes, guys. What do you think? How do you solve a problem like Maria? Skylar's got his calculator out. He's like, okay, I'll run the calculations. I'll get back to you. Skylar, let us know what you find. You're not? Oh, you're not on a calculator? Oh, that's awkward. That's awkward. That's awkward. Skylar, how do you solve a problem like Maria? We got all the shapes here. We got all your favorites. Square, rectangle, that guy. Let's look at this guy over here. You what? 7 centimeters. What about it? Words are hard.
Wouldn't it be the same on the bottom?
Isn't there like a country song? Something's on the bottom. Right? Isn't there? Anybody a country fan in here? Anybody online a country fan? Something on the bottom. I had a good weekend. I hope you did too. All right, so they're saying this is 7 centimeters. And the problem is, how do we figure out how long the whole thing is? How would you solve a problem like Maria? You said something on the bottom, right?
That side?
That side? The red?
Yeah, and then you just...
So we have an L. And if we just flip it, like down here?
Yeah.
So like...
No, down one more.
Down one more. Did I draw the same image as before? Let me make sure I didn't goof that up. Yeah, it looks like we're fine.
It's the same image.
It's a square, right? It's a square, so it's the same on every side. So you're saying I take this and I do it like here? Oh, I flipped it, didn't I? Wasn't that line over here? My bad, my bad. This was over here. My bad. I flipped our image. So you're saying if I take this... Ooh, okay. So conjecture. If that L is 7, then this L will also be 7. L7 squared, right? You know what that is? Geneva. Are you a fan of Lizzie McGuire? I don't know what that is, dude. I want you to go home and watch Lizzie McGuire. Hillary Duff. You know who Hillary Duff is? Dang. Your boy's getting old. That was like Disney Channel star back in my day. Okay. Okay. Now you got your Selena Gomez. Your Miley Cyrus. And your Hannah Montana. Wait, are they the same? I've never seen them together. You? Oh my god. So what you're telling me, conjecture, is that an L that looks like this is the same as an L that looks like that, or vice versa, right? You're saying they're the same. Now, how do you know that's the same?
Mine should be... I did the same.
Say it again.
I did the 3.
Ooh. Okay, got it. We're divided into 3 separate pieces. Yep. Oh, this is 4. My bad. Numbers are hard, guys. I'm struggling. And so good first hour, second hour. So those are the same. Yeah, I get what you're saying, right? They have to be the same. So you're saying I can take the individual pieces and do whatever I want with them. They'll end up being the same length. How do you know that's true? I was talking with my mom the other day, going, "Oh, those politicians, you can't trust them one way or another. They're always lying. They're saying one thing, he's saying the other. I don't know who to believe, so I just don't do anything." Right? That's a valid way of living, I suppose, right? I can't trust anybody, so I won't do anything. I won't make a decision one way or the other. But the problem with that for me is that not doing something is a whole lot less interesting than doing something. I was talking with another person the other day. Like, "Mr. Mack, what do you think about, what if you're wrong about how math education works? What if you're wrong about how to teach kids? Aren't there lives at stake kind of here? Like, isn't their education really important? What if you screw that up?" I hear that all the time from kids that say, "I don't want to be a teacher. I don't want to screw up kids' lives," right? Here's the thing. If my toaster is broken, and I take it apart to fix it, what's the worst that could happen? Wait, it's already broken, right? You see what I'm saying? If it's already broke, don't be afraid to break it. There's a saying like that, right? If it's already broke, don't be afraid to break it. Education's already broken. I'm not doing anything. But I have a chance of fixing it. If we break this up, we should be able to make it into anything we want and have it be the same length. That's our conjecture. That's what we think. Now, you can't trust them. Who knows? You can't prove it, right? Math could work that way. You could be like, "Well, you can't prove it, so we can't do anything." But here's the problem. There is a theorem. What is a theorem? A theorem is something that's proven. For sure. For sure. There's a theorem out there that says this in math, okay? Proven. You can't prove everything in math. I'll say that again. There is a theorem that we have proven using math that says you can't prove everything in math. We know for sure there are things in math you cannot prove. But yet, there's still math. You think of math as a science, but you're wrong. Math is leap of faith. Shooters shoot. That was Kobe. Shooters shoot. Well, I can't tell either way. Who knows, right? Sun's outside, can't tell if it's warm. Don't know. I just might stay inside. Sorry, can't make a decision, right? And it's true. Just because the sun's out doesn't mean it's warm. You been outside today? Is the sun out? See what I'm saying?
Freezing outside.
Right? There's something to what she's saying. She's right. They're both liars. I don't know, right? But at some point, you've got to take a step forward and go somewhere. Because otherwise, it's just boring. And that's what mathematicians said. Even though we know that we can't prove everything, at some point, we got to take a leap of faith so we can do something interesting. We call those leaps of faith postulates. Sounds like posterior. Nah. Postulates are assumptions, although there is something to that. Posterior, you know what posterior means? You know what your posterior is? It's your rump. The badonkadonk, right? Another country song right there. No go? When I say badonkadonk, do you know what I mean? You didn't grow up in the early 2000s with Toby Keith? Good, I'm glad you missed that a lot. Islamophobia. All right, so postulate, posterior means your butt, your rump, okay? Now, the reason I say it is because posteriors are this, postulates are that. Let me break it down. My English teacher used to talk about this for assumptions, right? Because we'd be in speech class. She'd be like, "You know what assuming does, right?" You know what she'd say? You watching? You know what assuming does? It makes a, out of, and. I'm going to say that again. Assuming, you know what it does to us, right? If you assume, it makes a, out of, and. Say it one more time. If you assume, it makes a, out of, and. And that's what a postulate is. It's an assumption. Posterior. Rump. You see where my mind goes? It's all connected. All connected. It's very intricate. So, we assume that you're allowed to take this L and turn it and have it be the same, right? Still the same length. Why are we assuming that? Because I can't prove that you can. But if I didn't know this to be true, could I do anything with math? No, I'd be like, "Oh, I can't tell. You can't be sure. You can never be sure with these things. Might as well just stay inside." Right? Mathematicians are like, boring. Let's make a postulate that says you can take this and move it around however you want. We call it the segment addition postulate, or if you're in my second hour, Corinne's postulate, because she came up with it. Segment addition postulate, or SAP for short. It says that if you take a bunch of segments, little pieces, right, and you add them together, you get the whole. And if you take the whole and you pull them apart and put it back together, it's still the same thing. Might look different, but it's going to be the same. Even if you rearrange these to this, they're still equivalent. That's segment addition postulate. How can I prove it? I can't. We just got to take a leap of faith because, like, good Lord. There's this guy named René Descartes, the Frenchman, Renaissance man. You know what I mean by Renaissance man from history? Name another Renaissance man. You know one? Da Vinci? When they say Renaissance man, they don't mean somebody who was born in the Renaissance. They mean somebody who was a jack of all trades. Da Vinci was a scientist, he was an artist, he was a writer, on and on and on. Sculptor, right? René Descartes was another Renaissance man, a man very learned. And he was a philosopher, as well as a mathematician. He actually gave us the Cartesian coordinate plane, that little thing over there, the thing you love and hate. That little plane. No, not like that. That thing. Little cross, right? And you can plot your points. Called the Cartesian plane because it's after René Descartes. But he said something even better than that. He said this phrase in philosophy. The question was, how do we know we exist? And René Descartes' response eventually was just like, you know what? I think, therefore I am. That's good enough. I can't prove that I exist, but because I think, we're going to call that good enough. That was his postulate. And now we can move on to better questions. This is a big deal for the time. This is boring. Of course it has to be true. Give me something interesting. If it weren't, it would break math, right? So we say, Now, some postulates later we prove aren't true. Or sometimes we prove that they're a theorem, that we can prove it. But postulates are neither proven nor disproven. They just must be true. And if they weren't, they'd break math. It's not really a science, guys. More like an art. Geometry, the thing you're in here for, shapes class, really isn't about shapes. It's about boiling down math to something that can be for sure. And when we realize that not everything can be done that way, we instead boiled it down to the simplest assumptions we can make. You don't want lots of postulates, right? Oh, well, just let it be true. Let it be true. Let it be true. Let's not think about that, right? Getting too smart. No, just trust me. No, that's not good. So we try to limit it to as few postulates as possible. Euclid has, depending on who you ask, 4, 5, or 6. Some people will be like, you only need 4. The other 2 you get for free. Vice versa. But there are 5 basic things for postulates in math that we build upon all math. They're Euclid's postulates. Some would argue 4, some would argue 6. Everything else is built from there. Some other people, other than Euclid, he's a Greek guy, come up with their own geometry, different postulates to base things off. The postulates are the leap of faith that allows us to do math. Theorems are built upon postulates or other theorems. Our first postulate is segment addition postulate. We're allowed to break apart a segment, a line into pieces, and it'd be the same. Now, assuming this is true, these are both 7. Skylar. Assuming that we're allowed to break them apart and put them back together, yeah, those are both 7, right? That's what segment addition postulate says. You can break it apart, put it back together however you want. It's still going to be the same, right? What about this? Well, this is 3 and then 1. This is 2 and then 2. Is that a problem? So you put an L there, like this. How long is that L? Just like the others, right? 7. You got overlap here. You got to subtract that. So we have to figure out how long that is. Then we get this middle piece we have to figure out, right? So if we know how long that is. Wait a minute. Hold on. Wait a minute. We overlap here. And we don't overlap there. And they're both a segment, aren't they? So one way to do it would be to add 7 on and then subtract however much that is. And then add however much that is, right? Well, why are we subtracting a segment and adding a segment? There should be an easier way, right? They should just undo each other. So 7 plus 7 plus 7 should be our answer, because this cancels out that. Right? Smell what I'm stepping? I'm going to say it again. We have an overlap here, so we have to subtract that much, right? But then we're going to add that much on later. Let's not say we did, right? 7, 7, 7, 21. That's clever. I'm gonna say that again. We have an overlap here. So we gotta subtract that, right? We don't want to count it twice. We already counted it in the red. We have to subtract that because we're counting it twice. But then we didn't count this guy. Notice how this and this has to be the same. So if we're subtracting that piece and then moving it over here, why not just count it? Segment addition postulate says that you can take 4 segments and arrange them however you want, even if they're not L's, and they'll still be the same length, right? That's really useful because imagine how we'd measure things in real life if we didn't have that, right? Imaginary land, we don't have a ruler, right? Because imagine a ruler, great. Is it too big, too small, right? I don't know. But in real life, how do I measure the length of the classroom? Well, you're going to need a ruler the size of your classroom to start out, right? No. You don't have to have the perfect amount. You can take little bits and add them together and make it, right? So if I take a small ruler or like this guy, I can measure my classroom with this, right? Because I can just stand them on end to end. Segment addition postulate says I'm allowed to do that. And you'll get the same amount. Think how annoying it would be if this weren't true. You want to measure that building? Great. You need a building size ruler. Well, how do I know how big to make it? I don't know. We don't know. We don't know how tall the building is. So you're allowed to break things up and move them around. That's what segment addition postulate says. Now you're like, okay, boring. We get it. This is really simple. But I'm going to show you some more problems and you're not going to know what to do. So when you take a look at this, ask yourself, do I understand what we're talking about here? Postulates are these leaps of faith that we build math upon. One of them is the simple idea that we can take a bunch of segments, connect them up, and it'll be the total, right? Or in reverse, take the total, break them up, and move them however we want. It'll still be the same. Okay. Where are your gods now? Let me pop this up. What about this one? How would you solve a problem like that? Take your time. This one's a rectangle. They say the red part is 18. What do you think? Geneva's got the calculator out. What do you calculate, Geneva? Are you figuring out how big each segment is? That's one way of doing it. Same thing as the last problem. Why?
Somewhat up there.
Okay, so if this is 18, you're saying this would also be 18? Okay. That makes sense. By segment addition postulate, we're allowed to take the individual segments, 4 segments here, 4 segments there. We're good. But now what? How do you know it's half? There's 2 instead of 4. When we do division, all we're doing is we're asking, what's the relationship between new numbers? We've got 4 here. What's the relationship between 4 and 2? Double, right? 2, when you times it by 2, you get 4. 4 is twice as big as 2. That's the relationship. Do you see how division shows the relationship? Division tells you the relationship. And you're like, well, I know that. Why do I need division? What's the relationship between 5 and 3? What's the relationship between 5 and 3? Not the same as 4 and 2, right? It's a different relationship. Ladies and gentlemen, fractions and division are the same thing. When we ask, what is 5 divided by 3? We're asking, what is the relationship between 5 and 3? You know the answer to that? 5 divided by 3? What's it about? Between what? What 2 numbers? 1 and 2, right? It's 1.6666666666666 repeating. Now, you don't need to grab a calculator, Skylar. You don't need to grab a calculator. You don't. 5 over 3. What's 5 divided by 3? The answer, if you want to be exact without having to round, because 1.666 you have to round eventually, right? The exact answer is this. 5 over 3. 5 divided by 3 is 5/3. That's it. That's the exact answer. They didn't teach you this in 5th grade? You get a hard problem, what's 5 divided by 3? Answer, 5/3. You'd look like a god. And your teacher would be like, wait, how did he do that? Why didn't you say 1 remainder 2? How did you know? Look at this kid. What's 99 divided by 7? 99/7. Oh my god. That's all it is. That's all fractions are. They're the easy answer to a division problem. And what is division? Relationship. How does 4 relate to 2? Well, it's double. How does 5 relate to 3? Well, it's 5/3 as big. Not quite double. A little bit less, between 1 and 2, right? The relationship between 5 and 3. Not quite double of 3. How do we know this is half? Because Geneva said 4 segments versus 2 segments is double. So 18 should have the same relationship to this. Let's call it x. As 4 and 2 have a relationship, right? 4 segments goes to 2 segments the same way 18 relates to what number? 4 and 2 have the same relationship as 18 and what? 9. In algebra, you had to be like, okay, cross multiply, blah, blah, blah. No. What does it mean? The relationship between 4 and 2. Remember, division is relationships, right? The relationship between 4 and 2 is the same as, that's what equal means, 18 and its relationship with what number? 9! This has to be 9. Okay. I see what you're saying. Wait, could you not see any of the stuff I was writing down? You did see it? This? Okay, good. What about these? Oh, you can't see that. Okay, good. Awesome. You weren't lying to me. What about this one? Where are your gods now? Segment addition postulate. Make a square. Ooh, I like that strategy. Do you see what he's saying here? I drew a really bad version of this, so we're going to look at that. You said it was 13 centimeters, right? Okay. Skylar, explain this. And dude, you need to write about this and get a grade, okay? See how frustrating this is? This guy was over there just like dropping threes. And we're like, okay, what we need you to do is write about that. And you're like, nah, I'm good. All we need you to do is sign the contract to go to the NBA. And you're like, nah, I do it for the love of the game. He's just back there dropping threes. Do this. Right? Get credit for it. He's like, no, I don't like capitalism. I don't want to make money. We live in a society, man. You need cash. We can have communist revolution eventually, okay? But right now, we're here. Make your money. Get that cash. All right, so here's our problem. Skylar, explain what you were theorizing. What was your conjecture of what we could do? Okay. So what does that do for us? So we don't know if it's a square or rectangle, do we? How long does this have to be, Housing Gay? I want you to think about it. I don't want you to answer. I said I want you to think about it. Okay? And if you have an answer, give it to me. I don't call on people like that. It'd be what? How do you know it's half? Take a look. Oh, sorry, you don't see what I see. I need to get my thing switched up. The reason I got this board over here wasn't for sound, actually. It was to be able to switch back and forth between cameras quickly. And it's not working. I need to fix it. Anyway, how do you know that this right here is half of this? Or in other words, that this and this is double. Or if you put them together, well, I need to stop saying it. Does anybody have something to say? I think I know what you're trying to say. And I think you should think about that and tell me. What do you mean 26? Well, why would you say 26? Something like that. She's onto something. I'm not sure if I agree with 26. Think about it, okay? You're onto something. You're onto something. How long does this have to be? Yeah, if you extend it down, how long does that have to be? This guy right here. Dumped you? Now, you mentioned something about half, right? Right? Who mentioned half? You did? Looks can be deceiving. In other words... Nope, not that one. It's this one.
Take it easy, assistant drawing.
I didn't tell you it was half. Couldn't this be like a third and 2/3? You see what I'm saying? We don't know for sure. Unless you know. Okay. Do you guys get that? This could be a third and 2/3, right? We don't know. It's just broken up. Right? We don't know if it's half and half. Just a drawing. How do you solve a problem like Maria? Skylar's right. One way is to extend the box down. Skylar, I want you to work on this. All of you. This one's mandatory. I'm going to get you journals pretty soon so you can play with your math. Later. Bye. People online, same for you. $13 does not relate to the one side. I don't know what you mean by that, Lily. Hi, Demery. You're only a little early, aren't you? Right? Isn't this 4th hour? Yeah, you're only a little early. We're about ready to start up. I just gotta spray down the desk. Bell just rang. Hi, Jeff. Hello. Good morning. Good afternoon. Not quite. Oh. You don't know if it relates to half the shape, unless you can prove it. Right. I would direct your attention to the board. If you have not met with me for portfolio review, that is the word bad. Because remember, at some point you guys do care about grades, unfortunately. I don't, but you do. Right? And if you haven't met with me, you don't have a grade in your grade book, or if you do, it's a really bad grade. If you have met with me, you probably have a pretty decent grade. You also will have a link in Skyward as a comment for that grade. Go to that assignment, you can look at the comment, and there's a link that you can copy and paste, and it will take you to the video of our portfolio conference. So parents are like, why my kid getting that? I don't believe that. You can take them to the conference and be like, see? Or why my kid get a C? Like, well, it's because your kid said they deserve one, and I didn't argue with them. They were right. And here's why. Take it away. You tell them on video why you deserve it. Great. Can you figure out sometime this week? Try and get this back. Because it's easy. Like, extra pencil or a pen? Hi. Hi, Lexi. All right, I'm going to do Tendy, but first I'm going to show you some of these problems. Again, if you have not met with me for portfolio conferences, you got to do that because that is your only grade. Grades are due Tuesday because we are halfway through the quarter. You guys do a midterm. I guess they do progress reports. Anyway, your progress reports are going to be going home. Grades will be due Tuesday for that. Doesn't mean they're permanent, but it means that we'll be heading out to your mom and dad. My plan is for people that have not met with me and aren't making appointments to meet with me, like we just discussed stuff, is to call mom and dad and be like, hey, it's really easy to get an A in my class. You just got to show up. How can we make this happen? Is a ride an issue? Like, what can I do? Internet problems where they can't do a portfolio conference. What Speaking of portfolio conferences, the plan is A-Day, B-Day. Every other Wednesday, we'll be switching between which kids have to do the conference. So next Wednesday, A-Day will go. Wednesday after that, B-Day will go, and vice versa, right? This will get us more time. That way it's not just me talking at you real fast for 5 minutes trying to rush to my next appointment. I did that from 8 a.m. to 3 p.m. Wild. Time flew by. But I'd like more conversation, right? And eventually I want you to lead it more than I do. Okay? So 10 minutes I think is a better thing. And the way I get that is instead of, lengthening the day somehow, go from 8 to 11. You guys in half. Which sounds just as fun as it is. What's the other thing? Post some stuff on Google Classroom. I want to show you that. More stuff you can write about in your portfolios. Some interesting questions. And while you ponder one of them, I'll be taking attendance. So people that are here online, I will be taking attendance soon. Just let me get to this. No, not this. Don't look. Don't look. Don't look. No looking. Okay, I posted a bunch of stuff. As you can see, there's some problems here and here. Here's a TikTok. Don't watch that. This problem, very hard to read. It says using only these 5 numbers, 10, 100, 1,000, 10,000, 100,000. You see the pattern. And using each just once, you're allowed to use plus, minus, times, divide, and brackets. Make the numbers so that they don't have any zeros in them. So you might be like, well, I'll just add them all up. Well, 10 plus 100 plus 1,000 plus 10,000 plus 100,000. Well, here's the problem, right? That doesn't work, does it? You get 111,110. Darn, 0 on the end. So close. A little challenge for you. Other problems that you might find interesting. Here's this guy. Sorry, I double posted. How would you do it? Be clever. What's your way of doing it? Calculator. Be clever. I know you can do it in a calculator. You're going to spend time doing that and then turn it in? Just a waste of everybody's time. You know what I'm saying? Calculator is always a valid answer, but like, who cares? If you're going to choose to do it, portfolio is optional. You can choose anything you want, right? If you're going to choose to do it, don't do it that way. It's a waste of everybody's time. You know what I mean? Here's another problem. Zoom, zoom. Basically, it says, I've got 3 circles wrapped like a bullseye, right? Concentric circles. Think like a ripple in the water. And they divide it in half for the first one. Can you draw a path that goes through? And it has to be a loop. Can you draw a loop that goes through every section just once? They show you for the first 2, right? This is divided in half, this is divided in thirds, that's divided in fourth. That there is a way to do it, and they've shown you. Can you always do that? How do you prove it? These are tough questions. I don't expect you to find the answer necessarily, but I expect you to try it if you want to, right? And then write about your work. Well, I found a path for 5, I found a path for 6, but obviously I can't keep doing this for every number. What's the pattern you noticed? Is there a pattern that you can prove happens that shows it always works? Or maybe it breaks. I don't know. Here's another interesting one. This one's so interesting it doesn't even have a question associated with it. The first question is, what are the rules? Hi, Jamie. I'll take attendance soon. Make sure you guys stick around. First of all, what's the question? They give you 3 examples. What does it mean? What does it mean? Hi, Gina. What? Okay, sure. How do you make a path that goes through every white square once without touching the purple square? Well, according to that conjecture you just made, well, that checks out. Why is there an X here then? How does that hold up with your thought of what the question is? What does the X mean? Not possible. Okay. Is that true? My first hour class thought of something clever. Remember, you don't ask. This does no yawning math class. There's no official question for this one, right? You have to think of your own. Well, they thought of a different one. It's very similar, and it actually makes the question easier, or the problem easier. What do you know about loops? What makes something a loop? It connects. Now imagine I start my loop, I don't know, here. Right? If I start there, what are my options? Up and on, or what? Over, right, to the right. If I go up, that's fine. Why do I know that's a fine move? Because what can I do next? I can go to the right. Cool. If I go here, that's fine. Then I got lots of options, right? Here's what one of my students said. In order to make a loop, you have to be able to go in and out of the square, right? Right? Eventually, if I go out, I have to come back in to complete the loop, yes? So if you look at this, this guy has an in and an out, right? This square right here. This square has an in and an out. It doesn't matter which order you do it in, right? This square has an in and an out and more. This has an in and an out. This has an in and an out and more. This has an in and out. This has an in and an out. Oh, look, there's my loop. Your version is going to start somewhere along here. However, we noticed there was options, right? See how we have options here and options here? Every possible solution is going to be some version of this. The only change is going to be how do you enter the middle, right? Because this guy, you only have one option. In and out, both these guys. This guy, you only have one option. In and out here. This guy, you have three options, so maybe you enter the middle, or maybe you don't. This guy only has two options, right? You got to take them both. The only change is going to be how do you enter the middle? Now let's take a look at that last one. This is actually very clever. There's a very famous mathematician named Leonard Euler. So famous that I named my plant after him. That should tell you something. The Bridge of Königsberg problem. And he actually thought of this brilliant idea to think about paths. That first hour came up with. Yeah. Somebody in first hour that wasn't my class last year came up with that brilliant idea of Euler. Look, you're thinking too hard. Paths, there's lots of options. Here's all the options. It works. What about this guy? The one they said it wouldn't work in. Why does this one not work? Logan. So whether I start or end here doesn't matter because I only have one exit or entrance, right? I can never come back if that's where I start. And once I get there, I can never get back to wherever I did start, right? Either this is an exit and I'm never going to get back, or it's an entrance and I'm not going anywhere, right? Impossible. Same thing with this guy. What about here? Possible or not possible? Oh, super easy, right? You can see the only loop you're able to make. And that's because, why is there only one loop? How do we know that there's only one way to make this problem? Every square only has two options, right? No other place you could go. Doesn't matter where you start. Notice how this is all three possible combinations. I don't need to do all the other squares, do I? Why? Why don't I need to check all the other squares? Like, what if the square is here? The purple square is there. Why? It's the same as this, just rotated. It has what we call rotational symmetry. Symmetry means the same after rotation. That's rotational symmetry, right? So this guy, we're saying, is equivalent to this question, right? These two are equal. Not all things have rotational symmetry. If you solve this one, you've already solved this, right? That's the beauty of symmetry. It simplifies stuff. In fact, there's 1, 2, 3, 4 versions of this that we've solved, right? All four corners. This one solves the middle, and then this one solves these guys, right? None of those would be possible. Rotational symmetry is super useful. And again, not everything has it. For instance, your boy, I don't have rotational symmetry. If you turn me upside down, right, I'm not exactly the same, which is what most of my students describe me as, different, right? I'm not the same if we rotate. Although one might argue that I'm still the same person, even upside down. All right, I bet with the teacher, if I stood on my head, there'd still be some kids. Dollars. Well, how are you gonna keep? You gotta keep them off their phones. You gotta. Lady, I'm gonna bet you $10. I could stand on my head in the middle of class. They still wouldn't pay attention. They have to want to. I win. Easy $10. $10 times 5 classes. You do the math. All right, so I got a problem for you. Because somebody the other day was like, when are we going to get to the shapes? Isn't this shapes class? I was like, you know what? Person who sounds like this, and they do. They really, you know what I'm talking about, right? You know what? You're right. If you want to do that, we'll do it. So here's some shapes for you. I'm going to zoom in. Zoom. Zoom. There you go. We have all three flavors of shape. Square, rectangle, and that guy. While you're pondering how to solve these problems, which you're more than welcome to access any paper. My paper got stolen from me. I used to have a big thing of paper up there. But if you want any graph paper, I'll throw some over here. If you want to mess around with it, go ahead. If you just want to think about it, whatever. I'm eventually going to get you some graph paper to binder, kind of like I have, where I do all my math notes and playing with math for you guys to play with. But I don't have it yet. I got to go get a lot of binders. Let's take some attendance. So who did I see? I see Demery, Lexi, I see Olivia, Andrew, and Jamie. I do not see Gage, but everybody that's supposed to be here in class is here. What do you think about this? You want to look at the one on the left first? Or is that too boring? Remember, anything we do in class you can write about in your portfolio, and it'll count as your only grade for the year. You what? I also said there's one post you have to do for this next conference that has to be about addition, subtraction, or multiplication, your choice. But you can also supplement it with other stuff. Don't just think, oh, I did my post on addition, that's an A. Not necessarily. And do you have something to say, or are you just messing here? Okay. No? Okay. Gina's busted out the calculator. She's like, I'm going to get this. I'm going to do my calculations, and I'll get back to you guys. Gina, what have you found so far? Nothing? Is the calculator not useful? Oh, my bad. That's embarrassing. Sorry. That's not what they drew. Booby. You seen that one Vine or whatever video? The guy's just like, and he's like missing all of them. That was me in middle school. I didn't play basketball. Shoot or shoot. All right, here we go. I'm gonna draw a picture, and Logan is like on fire today. But Logan, speaking of basketball, that's for you, buddy. All right. Oh, you ready? Oh. I think the mics picked that up. For everybody watching at home, that sound that you heard was Jordan's back cracking. Logan, what do you have to say? How do you solve a problem like Maria? Okay. So every 4 spaces you're saying is 7, right? 7 centimeters. We can just count the individual ones. How do you know that we're allowed to do that? How do you know that we're allowed to count and 4 like this is the same as 4 like that? Now, I drew this really poorly, but... what you're saying is that this is the same as this. How do we know that's true? Yeah. What about it? All squared sides are the same. That's true. So this side should be the same as that side. That means 3 should be the same as 3. So we know for sure, by definition of a square, that this is the same as that. So it looks like it has rotational symmetry, right? No, I won't do it. Okay. So that means this and this. Okay, that's a good idea. How do we know for sure? It's a square. This works. But how do we know it works for 4 as well, even when you bend one of them? We call this as a postulate. A postulate is an assumption. When I say postulate, do you think of like posterior? Do you know what a posterior is? Your posterior is your rump, your badonkadonk, that dump truck, right? That's what it is. Posterior postulate. It's an assumption. Do you see where I'm going here? You probably don't. My English teacher, she was my speech teacher. She used to say when we'd write our speeches, when you make assumptions. Yeah, he's pulling out the calculator. When you got assumptions, when you assume something, it makes a out of and. I'm going to say that again. When you make an assumption, it makes a out of and. Say it one more time. When you make an assumption, when you assume, it makes a out of and. I used to say that all the time. But here's the thing. In math, we have these things called the postulates. We're basically assumptions. We're saying, look, this is the same as that. It's okay. You can take a bunch of little pieces and rearrange them, and they'll still be the same length. How do we know it's true? Well, because it has to be. Funny thing, postulates, they're not proven, but they just gotta be, right? Theorems, on the other hand, are proven. But here's the thing. You want to know a fun theorem? You know, the science of math, right? Everything's proven. It's very rigorous. There's a theorem called Gödel's incompleteness theorem, which says that math is incomplete. And what does he mean by that? He means that there are things in mathematics that are true that we cannot prove. I'll say that again. We have a theorem, something that's proven, that says there are things in math we cannot prove but are true. It means at some point you have to take a leap of faith, even in math. And if you don't, you can't do anything. I was talking to my mother. First mistake, okay? Talking about politics. Second mistake. Well, they're both liars, you know. All politicians lie. They lie on this side, lie on that. I don't know. I don't know who's true, so I don't do anything. You know, can't do anything. Don't know. Can't tell. It's like, well, that's one way to live your life, right? I can't tell. Is he right? Is he right? Who knows? I'm not gonna do anything, right? Sun's outside. It's shining. What do I wear? I don't know. Just because sun's out doesn't mean it's warm out. I don't know. I don't know. You guys go outside today. Sun's out, not warm, right? She's right. She's not wrong. That's not my point. My point is there's two ways to live your life. One way of, I can't tell, so I just won't do anything. And the other way of, you know what, I'm going to take a leap of faith here. I'm going to take a step in a direction. Mathematicians decided to do that. We can't prove everything. We've proven it. At some point, we have to take a leap of faith. Now, mathematicians don't like taking lots of leaps of faith. You can't just be like, oh, it's close enough. I'm sure it's right. I'm sure it's right. You can't just do that your whole life. That's not going to work, right? So what they did is they tried to limit as few postulates as possible. Euclid has 4, 5, or 6 in his geometry, where everything boils down to that. Those are the big leaps of faith. Everything after that is proven. Either using those leaps to prove it, you could take something apart and put it back together and it's still the same, right? That's a postulate. We're going to talk about that in a second. Or other theorems build into other theorems, right? I proved this earlier, and that means this, thus, right? So postulates are assumptions. We try to limit them as much as possible because they make out of. But one of the postulates, if you're in my second hour, would be Corinne's postulate, because she kind of came up with it today, but someone beat her to it. Euclid did. He calls it the segment addition postulate. And you can call it Corinne's postulate if you want. Segment addition postulate's fun because it's SAP, S-A-P. And what it says is that we're allowed to take pieces of a line and rearrange them however we want, and at the end of the day, they're still going to be the same length. This should make sense to you. When I want to measure the length of my classroom, I grab one of these. Is this the length of my classroom? No. Can you imagine? How do you want to measure the classroom? Well, first thing you got to do is find a ruler that's the same length as your classroom. Lay it down and you go, okay, right? Well, how long of a ruler do I need? I don't know. We don't know the length of the classroom yet. Right? How do I measure that building? Well, you need a building size ruler. No, you can take pieces, right? And lay them end to end, and you'll be able to get how long it is. This makes sense. 4 pieces. Doesn't matter how you arrange them, all are going to be the same. This is the same as that. That's segment addition postulate. It seems obvious, but I want to be honest with you. There's no way to prove it. We just have to assume that it's true. And I take those very seriously. I don't want to make a... So postulates aren't proven. They're leaps of faith of math. The thing that math is built upon. Leaps of faith. Assumption. Theorems are built from either postulates or theorems, right? Things that were proven initially, or they go all the way back to the OGs, the foundation postulates. We have corollaries, things we get for free. So once we know that this is the same as that, don't we also know that that is the same as that? Right? You don't have to have a different rule every single time. You don't have to prove it for everything. There's this thing called symmetry. Corollaries are things that, look, you get that for free. This also means that. Smell what I'm stepping in? How do we solve a problem like Maria? This is 7 and this is 7. According to segment addition postulate, we're allowed to flip our 7s, or our L's. Are they L's or are they 7s? I don't know. How do we solve this? Be clever, yeah. 7/4 times 12. Where'd you get 7/4 from? Check this out, check this out, check this out. He's figuring out how long this individual segment is. He's saying, look, what's the relationship between the number of segments and how long they are? How long is this? How long is this red part? 7 centimeters, right? 7 watermelons, 7, no. When we show relationships in math, one of the best ways, one of the ways we have not taught you before, is we show it through division. What's the relationship between 4 and 2? Well, division tells you the relationship. It's double. And 4 and 2 have the same relationship as 6 and 3, don't they? It's double. Now you're like, well, that's obvious. But what's the relationship between 5 and 3? Is it the same relationship as 4 and 2 and 6 and 3? No. What is the relationship between 5 and 3? It's about what? Times what? What do I do to 3 to get it to be 5? It's about times what? Between 1 and 2, right? The relationship between 5 and 3 is about 1 point, I don't know, 6666666. Oh my God. Do you see I have to eventually round there? The relationship between 4 and 2 is a nice relationship. It's 2. You know, like that one couple, they're like meant to be together. 5 and 3, kind of an odd couple. They're like that one group, and you're like, girl, why are you dating him? He's bad for you. And she's like, well, hot, okay? I just want to give it a go. I just want to try it out. And then you're like, but like, you're a good girl. And she's like, well, I'm not that good. And you go, Sarah! Right? You ever had to have that talk with one of your friends? I can think of a specific one last year. That was disgusting. All right, but we avoided that bullet, okay? Y'all been there. 5 and 3 are a weird relationship. You have to round eventually to make it work. Don't settle, honey. You can do better, okay? The relationship between 5 and 3 is 5/3. 3 is 5/3 smaller than 5. 5 is 5/3 bigger than 3. That's the relationship. Fractions, ladies and gentlemen, are just answers to division problems. The easy answer. What's 99 divided by 7, Mitchell? 99 over 7. 99 sevenths. Actually, it's a blah, 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 remainder too. No. It's 99 over 7. It's exact. You don't have to round. You don't have to do anything. Relationship between 5 and 3. What's 5 divided by 3? It's 5/3. You never have to use a calculator in here. Not because I don't let you use it, but because it's a waste of your time. Why plug that into a calculator to get an answer you're going to have to round? An answer that's an estimation. When you could literally just get the right answer. 100%, no rounding. Anyway, 7 and 4. Not a nice relationship. But that's the relationship here, isn't it? 7 is how long it is with 4 segments. Now he's saying we have a relationship of 7 to 4, and we have 12 segments, right? And that's how you can find your answer. 7 and 4 here, 7 and 4 there, but we got 12 of them, right? It's kind of weird. 3, 3, 3, and 3. How do you solve a problem like Maria? How did you do it? Don't know? Is that where you left off? 7/4 times 12. The relationship here, but done 12 times, right? How'd you do this? Or maybe you didn't yet. You have an option. I don't think you guys know this. You can either times the top together or divide the bottom, whatever you want to do. He times the top. What's 7 times 12? Ain't nobody got time for that. Let's divide first. What's 12 divided by 4? What's 3 times 7? If you did that in any of your math classes without having to, you know, well, this right here is over 1, and we 4, and then we win this number, and then you divide, right? Your teacher would think you were a god. How do they do it? Really easy. You either times by the top or divide by the bottom. It's up to you. I divided first because that's easy. 3 times 7 is 21. Done. This whole thing's 21, according to this. If the relationship holds, that's 7 for every 4, right? And there's 12 of them, so 21. What's another way to do this? That was really mathy. Is there another way? How do we get this bit right here, this green part? It's different than the blue and the red part, because why? Why is it different? Yeah, Maddie. It's 2 and 2, not 3 and 1. Now, we assumed earlier that 3 and 1, no matter how you do it, is fine. You can do it like this, you can do it like that. So segment addition postulate says, in theory, this should still be the same, right? Assuming that that's how math works. Again, that is a big assumption. But let's do it. So how long would this be, Maddie? Gotta be 7, right? 21. Another way to do this, another student thought of this last hour. I thought it was brilliant. Instead of doing this, they put the L here, right? Which is just a normal L. And they said, look, there's overlap, right? Overlap of 2. So I got to subtract those 2 segments, right? And then I won't count them twice. See how I already counted them with red? I counted these 2 with red. Are you with me there? But I need to add on 2 later. Wait a minute. If I need to subtract 2 because I overlapped, and then I need to add on 2 later, how about we don't say we did, right? You see how the red is 7, the blue is 7, and this is 7 as well, with an overlap of 2 and then missing 2? Why subtract and then add when you can just say, look, that overlap is just going to take its place down here. That's another way to know that it has to work that way. Is this too easy? Boring? It is, isn't it? Okay, next problem. Where are your gods now? I know you want more problems. Where are your gods now? How would you solve the second one? Notice that it's a rectangle. What's the difference between a rectangle and a square? All the sides don't have to be, but they can, right? This guy right here is a square, but it's also a rectangle. It's just a perfect rectangle. We have a special name for that. It's called a square. Rectangles are oblong. Have you ever been called oblong before? Longer than you are, or taller than you are wide, or wider than you are tall? I hope you haven't. Very cruel world. Wait, hold on a second. The bottom part, okay. So they give you this. And I tell you it's 18. How do you solve a problem like Maria? Remember, we're allowed to use segment addition postulate. We're allowed to assume that you can take the segments and rearrange them, right? And they're still the same length. Jackson, I'm glad you're here today. You had an idea? You're still thinking. Take your time, please. I don't want to rush you. Yeah. Logan, you got something to say? Are you seeing the L right here? Okay, gotcha. So that's also 18. That's fair. That's literally the same. That's pretty easy to be like, trust me on that, right? Why divide by 2? How do you know it's half? Aha! So the relationship between 4 segments and 2 segments, that's what we're asking about, should be the same as the relationship. This is an algebra problem that you guys used to struggle with. You're never going to struggle again. The relationship between 4 segments and 2 segments is the same as 18 centimeters to its relationship to what? I'm going to say that again. Division is relationships. So when we read this problem, don't be like 4 divided by 2 equals 18 divided by x. No. 4 and 2's relationship is the same as 18 and x's relationship. What's the relationship between 4 and 2? Double, right? Twice as much. 4 is twice as big as 2. What's twice as big? What 18 is twice as big as what? 9. Before you get this, you'd be like, yeah, 9. Before we get this, and you'd be like, why we cross multiply? We get to carry the x. What? No, God. Think about what it means. 4 and 2 has the same relationship as 18 does with x. Well, x has to be 9, right? It's because it's double and half. You know I'm kidding, right? You know? Okay, good. Play a character. Back on! Character's back on. All right, so. How would you add these numbers? I get out a calculator. Great, awesome. Give me something interesting, something original. Some way that makes it easy to add into my head. Troy. I'm asking if you have any ideas. It's totally fine to say you don't. Okay, here's what I want you to do. I want you to think about it. When I call on you, don't assume I'm asking you to give me an answer. I'm asking, do you have an answer? And if you don't, I want you to think about it and get back to me, okay? Like right now, Troy's thinking about this while I'm talking with other people. Think of a clever way to add those in your head to make it a little bit easier. Yeah, go ahead, Troy. 8, 8, which is 16. 10 and 10 is 20, right? And then 9. So we have 16 and 9. Does anybody know what 16 and 9 is? What's 16 and 9? Guys, 16 and 9 is the same thing as 16 and 10, but then minus 1.
25.
16 and 9 is 25, and then we have 2 10s. 25 plus 2 10s is 45. Another way to think about it, 9 times 9 plus 9 plus 9 plus 9 plus 9. How many 9s is that? 9, 9, 9, 9, 9! I was really hoping you'd pull that out. How many 9s is that? 9, 9, 9, 9, 9, 9, 9, 9, 9. So 9 times 5, which is? How do you know 9 times 5 is 45? Because I have it memorized. I do the finger thing, right? Use the clock? Yeah, exactly. What's another way? How do you know 9 times 5 is 45? What's 5 times 10? So 5 times 9 must be 5 less, right? 5 times 10?
Yeah.
Because 5 times 1 is 5, and then 1 times 10 is 10. 5 times 1 is 5 times 10 is 50. I don't know. Eventually you have to take a leap of faith, right? Postulate. Okay, where are your gods now? Last one, and then I'll stop. This one I want you to write about in your portfolio, definitely. Okay, this is kind of mandatory, quote unquote. I don't know how I feel about that. Mandatory-ish. We have all 3 flavors of shape: square, rectangle, and that guy. How do you solve a problem like that guy? Let me draw it real quick. If you want to draw, there's paper up there and markers. You don't even have to draw what I ask you to draw. You can just draw. Came up with some pretty smart ways to solve this in one of my classes. Ask Skylar Drolamo about that. The dude's back there just shooting threes, but he won't write a portfolio. It's like the guy that's just like nailing every shot, and they're like, we want to sign you to a deal. And he's like, oh no, I do it for the love of the game. Get paid! Yeah. Oh, sorry, hold on. What'd you say? Okay, so Logan is saying this should also be 13. Why? Because he is saying, look, I made a rectangular square or something out of that. Okay? So this has to be the same as that. Okay. How do we subtract that out of there? That's one way to think of it. Keep going. Write about it, okay? Don't do it. I do it for the love of the game. That's you. You're Skylar Drolama. You're back there on fire. See you later.
That's Skylar.
Bye. Write something. People that didn't do their portfolio stuff, we need to meet so you have a grade.
Thanks.
When? Well, it's supposed to be last Wednesday or Thursday or Tuesday. As soon as possible is when we get to the grades for report cards are going to be out tomorrow. Hello. Yeah, but that's fine, but how do you know repeating numbers exist like that? How do you know that those are valid? How do you know they must exist? I don't really like root. One of these days I will try to solve it, but the way I want to do it is not look up a solution. Huh? Yeah, of course. Like most people just look up the way to do it and then memorize it, which I think defeats the purpose. There's no inherent fun. At least not for me. Hello. One of these days I'm going to mess with it and learn how to do it and figure out how it works, but I just haven't had time. Recognizing a pattern that continues, there are lots of patterns that continue. That doesn't mean there has to be numbers that repeat forever. So for instance, Lily, how do you prove that root 2 is irrational? Because that's what we're talking about, right? How do we prove that there are numbers that go on forever? How do you prove that root 2 is irrational? If you can prove that, then you know that there are numbers that go on forever, never repeat. I mean, 0.3 repeating does repeat, but getting the irrational ones, pretty easy to prove that ones that do repeat that go on forever must also. One begets the other. All right, folks. Hey guys, I'm gonna turn off the stream really quick. Actually, you know what? Let's forget it. Let's forget it. I won't do it. Hey guys. Yeah, I like straight up in. And they were roommates. It is. We missing McChicken? Haley? Haley McChicken, are you online? We have both McDonald's. Anybody seen Camden? Or Leah? I mean, we're early. I would direct your attention to the board. For those of you that aren't here, I don't have my camera hooked up yet. I have the stuff at home. I forgot to bring it in today. It says grades are due tomorrow to be sent home for report cards. So if you care about grades, I don't, but you probably do. You want to make sure that you've had your conference with me because that's our only grade so far. After this, we'll be doing conferences every other week. 8A people will go next week. Not this week, but next week 8A people go, and then BDA people go after that, vice versa, right? On and on and on. And that will allow us to have some more time to talk instead of 5 minutes and I got to rush to the next appointment. Eventually, I want you guys doing more talking than I do. I want it to be kind of your thing to lead me through. So as we go on, I'll... Eventually, I might even have it where you do conferences with each other instead of with me. And then record it. Speaking of the recording, if you did a conference with me, you should have a grade in the gradebook. Okay, so check that out if you want to. Algebra kids, half of you have the video up on a link. You do. The kids that went earlier have it. The kids that don't, it's because Google's still waiting to upload it to Drive. And once it's there, I'll post the link. So that'll be done tonight. Hi, Leah. Exactly. What's up, Camden? All right, so we got everybody except Mac, it looks like. Mac, Haley, and McChicken. So yeah, grade should be up for you. If you did a conference with me, I recorded it and put it as a link. Some of you don't have the link up yet because it's got to go to Google Drive. It's uploading at my house where I have lightning fast internet, but Google's being dumb. You know you got fast internet when Google's the thing that slows you down.
Friday, please. And come on Wednesday, please make come to the front door only. Zero Point Parking, please have it.
Let me use the restroom while we wait for announcements. You guys can hear the announcements, yeah?
Exercise. Consider getting a group of your friends together and pitching in. Expect that the person knows you volunteer to earn 2 code points. You get 10 years to dog park. Contact Mark Specialist for additional information. SSA dues of $20 are used in this culture by Friday, September 25th. If you have any questions about SSA membership, please contact Ms. Culture. And quote a week, one kind word can change someone's entire day. Have a great day, Anisha.
Sorry to keep you waiting. Alright, so. Oh, McChicken is here. Ah, well, I'm glad we waited for you. Anybody seen Haley? If you're friends with her, send her a message. Looks like we do not have Mac. So, McChicken, if you want to contact Mac and get him in here, that'd be great for me. Alright, so. That's an A, by the way. Do any of you guys write your A's like this? You do? Okay. The girls that used to bully me in middle school would write their A's like that. Yikes. Yikes. So you can write them like that if you want, because it looks less like a 9. What do you know about A and B? If this is true, so if A plus 5 equals B, what do you know about A and B?
Good number.
Dan?
They can be any number.
It can be any number. Why do you think that?
A could be any number, that
Okay.
doesn't give you an answer.
Right.
It says anything plus 5.
So A could be 7 and B could be 2. Why not?
Because they don't, the problem has equally.
So 7 and 2 would get. Okay, gotcha. So hold on. We have 2 statements here. Okay, I'm working with you. Okay, I hope you don't mind me questioning what you're talking about. Hi everybody. A can be any number. B can be any number, right? We agree with that? But what happens as soon as you decide upon a number for A or B? So infinite possibilities. But as soon as I say A is 5, what happens? B has to be 10. It gets locked in. They're linked together, right? And we show that link by showing a coordinate, right? You guys probably talked about this, right? Comma, or parenthesis 5, comma 10, right? Parenthesis, that thing. X goes there, Y goes there, you know, whatever. All it's showing is that they're linked. 5 and 10 with this is linked. If one's 5, the other's 10. If this is 10, if B is 10, infinite possibilities, but if B is 10, what happens?
It's 10 and it's 5.
It has to be. Do you see how they're linked either way? One decides the other. They're linked. Infinite possibilities becomes instantaneously one idea. Like a reverse Big Bang. Big Bang starts at a tiny little point and then infinite here. We take the infinite, and as soon as one thing happens, we know exactly what's going on. You guys know much about electrons, particles, like little things flying around? There's a thing called the Heisenberg uncertainty principle. And I'm going to butcher it. But the idea is that if you know which direction a particle is moving, you cannot know its location. So I know it's heading north, but where is it right now? No idea. There's no way to tell. The reverse of that is also true. I know the particle is right here. Okay, but where's it going? I have no idea. You can't tell. If you know one, you can't know the other. This is the opposite. If you know one, you automatically know the other. We have infinite possibility. As soon as we look at one, boom! It condenses to a singularity. We call that singularity a point. It has no dimension. Think about that. It's a dot. How big is it? It isn't. You ever done that? Someone asks you, okay, how big is it? And you say it isn't. I hope not. So that's what a point is. It has no dimension, has no size. Does it exist? Yes. Where is it? Right there. I know where it is. Location. But if I know the location, I don't know how big it is. I'm going to say that again. Here. A and B can be anything, right? So I don't know the location, do I? But I know how big they are. Humongous big. Are you smelling what I'm stepping in? A and B can be anything. Infinite possibilities. That's how big it is. But I don't know its location. But as soon as I know its location, 5, 10, automatically, I know where it is, but it has no size. Infinite possibilities. That's infinity. That's the size. The location? Don't know. Right? Infinity. Everywhere, but also not everywhere. It's like humongous big. A point, I know exactly the location, but the size? Super small. Even smaller than that. So small we can't even call it small. Size? It's not. Infinite possibilities represented here. And as soon as we find out one part, we get the other. And it takes infinite and condenses it down to one spot. Infinitely huge, but we don't know where it is, to exactly where it is, but we don't know what size it is. I think it's interesting. What else do we know about A and B? If A is 5 and B is 10, what else do we know? Come on, don't be afraid. People online, don't be afraid. Are difference quotients and derivatives the same thing? They're variables. I don't know if difference quotients, I don't know that term exactly. They could be literally the same thing. But I think they're just very related. What else do we know about A and B? Right? That's what this means. What else do we know about A and B? What if A equals what? Infinite possibility. 2. Then B must be 7. What do you notice about these numbers? A equals 6, B equals 11, right? We can go on and on. We've got 6, you've got 11. On and on and on. What do you notice about these numbers? Hey, Mac. 5 and 10, 2 and 7, 6 and 11. Yeah. They have a distance of 5, don't they? Wait a minute, distance? What is distance? Distance is how far it is away. What else is distance in math class? How do you find the distance between 7 and 2? How do you find the distance between 9 and 4? How do you find the distance between 10 and 5? You subtract distance subtraction. Wait a minute. Where's the subtraction here? Hello? Hello? It's addition. Where's the subtraction here? You said distance is a subtraction, right? The distance is always the same. How do you find the distance? You subtract it. Where's the subtraction? Where's the chapstick? You ever seen that? Way too long. No, you have? Okay, well, watch it. Where's the subtraction? I can go even older. Where's the beef? Where's the subtraction here? You say the difference between, the distance between A and B is 5 always? So you're saying the distance between A and B
minus 5 equals A.
B minus 5 equals A. You're saying these are the same thing. I'm very echoey. Okay, let me turn it down. I'm trying to get it to where you can hear the kids. All right. B minus 5 equals A. There's your subtraction. Are these the same? This says the distance between 5 and B is A. Yeah, you know that because of PEMDAS, right? That's how you came up with it? That's good. We're going to come back to that. That's actually really advanced. I know it seems silly. I know it seems silly. You said the distance between A and B is always 5. Let's look at this. Distance between A and B is always 5. How did you find the distance between this? You subtracted them, right? You did B minus A, and you got 5. What about this one? What'd you do to find out that the distance is 5? You did 7 minus 2, otherwise known as so apparently, this right here isn't just A plus 5 equals B. It also implies B minus A equals 5. They're the same. They have to be, right? We saw 5 and 10 are separated by 5, 2 and 7 are separated by 5. How do we get those numbers? We got it from this. They're always separated by 5. So, Haley's right. We can use PEMDAS to move stuff around, and it's always the same. But how do you know it's the same? See how this naturally popped up? We just did it from looking at our numbers. Getting from here to here, what do we do to get from here to here if we're thinking in PEMDAS? What do we do? Haley, what do we do to get from here to here if we're thinking PEMDAS? We got this from just looking at our numbers, right? Whenever we do B minus A, 10 minus 5, 7 minus 2, 11 minus 6, we always get 5. So this has to be true. And how do we get these numbers? We got it from this. So this must also mean this. They're separated by 5, right? How do we get from there to there PEMDAS-wise? What do we do? How do we get from here to here using PEMDAS? Because they're both the same, right? They're saying the same thing. This got us 5 and 10, 2 and 7, 6 and 11. Another way to represent that is to say that B and A are separated by 5 always, right? So this must imply this. That means if PEMDAS is true, we should be able to get from here to here. What do we do? A little tricky, isn't it? What do you notice about this one and this one? How do I get there, though? Aren't you solving a Rubik's Cube right now? Well, that Rubik's Cube is the same as the one that's finished. You just got to rearrange them. Oh, very good. Very good. Oh, wow. Let's move on to the next problem. We've solved the Rubik's Cube. You just got to rearrange it. How? And it's side to side. You notice how A and B aren't together here, but they are together here? We need to get A and B on the same side. How do you want to do it? How do you go from this to this? We want B and A to be together on the same side. How do you want to do it? Well, children, we either have to move the A over there or the B over here. How do you want to do it? No wrong answer. It'll always be the same. Can't mess with a Rubik's Cube and be like, oh no, I think I broke it. No, it's still fine. As long as you didn't take the pieces out, you're fine. B plus A equals 5. Let's talk about that. B plus A equals 5. What is this saying? This is saying that if you take A and add 5, you get B. So for instance, if I have 5 for A, I get 10 for B, yeah? What happens if I have 5 for A down here and 10 for B here? Uh-oh. Not the same, is it, Kaylee? See how if I have 5, I get 10? So if A is 5, B should be 10. If this is the same, if A is 5 and B is 10, uh-oh. You see the problem? So it's not the same. You can put them back if you know how to put them back correctly in a Rubik's Cube. But then at that point, you can actually screw it up. Again, you can do anything. Same thing with math. You can just randomly put stuff back together. But it's not safe. Same thing with the Rubik's Cube. You can take it apart and put it back together, and then it's unsolvable. That can happen. How do we get A and B on the same side? Can't, huh? Why not? Come on, PEMDAS warrior. Miss. Oh, I got this. Easy. Easy problem. Uh-huh. So you said like this, right? I didn't get A and B on the same side. Come on, why can't we bring them together and cooperate? Question. We know the goal is to get A and B together. Do you want to move B over to A or A over to B? Make a choice. B to A or A to B? B to A. That's a positive B, right? In order to move stuff, again, we're not moving. That's just an illusion. We are only allowed to do the same thing to both sides, right? So if I subtract B there, I have to subtract B here. And that's the same problem, right? 5 plus 5 minus 10 would equal the same thing as 10 minus 10. Agreed? So we didn't change the problem. It's still valid. But now we have this. I'm going to put the B next, right? Again, keep the sign with the letter, right? Plus 5. What's over here? What's over here? 5 plus 5 minus 10 equals 10 minus 10, right? 0. Anything minus itself is 0, right? And this is still a valid statement, right? We didn't change it. 5 and 10 will still work here. 7 and 2 will still, 2 and 7 will still work here, right? 2 minus 7 is negative 5 plus 5 is 0, right? Any number separated by 5 will still work. We didn't change the problem. Okay, now what? We got A and B together. We want to show that if you take A and B and subtract them, you get 5. You see a problem, don't you? We're going to get this. Now, wait a minute. They're not separated by negative 5. They're separated by 5. Right? 5 and 10, 7 and 2, 11 and 6. They're all separated by 5, not negative 5. What do you notice about this and this? The direction is switched, right? 7 going to 2 is minus 5. 2 going to 7 is positive 5. So we want B minus A. We got them together. So apparently this should be the same as that. This direction. Okay. We tried getting B over to A. That's valid. We did nothing wrong. It's just not what we wanted, right? Like when you move a Rubik's Cube around and you make like a cross on every side, right? That's great, but it's not what we wanted. We wanted it solved, right? So how do we get B minus A equals 5? Well, again, we need B and A together. We tried moving B to A. Let's try moving A to B. How would you do it? Yeah, Cameron's right. This time we're going to subtract it. So A plus 5 equals B. So this time we're going to move the A. We're subtracting A from this side, subtracting A from that side. Check. 5 and 10 worked before, right? 5 plus 5 minus 5. That's 5, right? Equals 10 minus 5. That's 5. Yep, we're fine. We didn't break anything. One of the rules of algebra is very simple. As long as you do it to both sides, it's fine. Okay? As long as you do it to both sides. That'll keep it balanced. So now we do this. A minus A is what? We can do it in any order. A minus A is 0, right? 5 minus 5, 10 minus 10, whatever it is. It's going to be 0. So all that's left over is 5 on this side. And B minus A is over here. Another way to write that is just to flip the whole thing, right? 5 equals B minus A equals 5. Doesn't matter. Potato, potato. The difference between B and A is 5. And that's the same as saying A plus 5 equals B. Of course it does, right? Any number that you add 5 to gets you another number. Great, they're always going to be separated by 5. 5 and 10, give me another solution. Do you need to look at the math? No. 5 and 10 would work. What other numbers would work? For B and A. 7 and 2, what other numbers? Oh, come on. 100 and... I lost you, Kaylee. This says you take a number and add 5, you get the second number. Another way to think of that is saying those two numbers always are separated by 5, right? See how it's the same? So give me two numbers that are always separated by 5 and it'll always work, right? This way is easier to think about, I think, right? If I tell you, take a number, add 5, and get me another number, you have to go 100 minus 95? Yeah, so 195 would be separated by 5. Yep. 67 and 62, right? Again, infinite possibilities, but as soon as we choose one, there we go. And if you were to graph this on a number line, right? Here are all the possibilities. You said 5 and 10, right? So here's the answer. Here's the distance. 5 and 10 would work for A and B. But also you said 7 and 2. And those distances are the same, right? They're all 5. You see how graphing every possible answer would get really messy really fast? And that's without even using decimals. 2.2 and 7.2 are separated by 5. Really gross. So eventually you'd end up coloring in all of this, wouldn't you? With a lot of little breaks. That's messy. Not very useful, right? What else do you know about A and B before we get on to how messy this is and how to fix that? If A plus 5 is B, what else do you know about A and B? Question. Whoops, sorry. If A is 2, B is 7. If A is 3, B is 8. If A is 4, B is 9. Not only are they always separated by 5, but what else do you notice about A and B? A is 1, B is 6. A is 2, B is 7. A is 3, B is 8. What other relationship does A and B have? This is kind of an obvious one. Haley, what do you notice about A and B here? It's a really obvious relationship. A is always what? It's always 5 away, right, from B, but even more obvious than that. A is always... It's always smaller, isn't it? In other words, A is less than B, always. Always. B is always the bigger number. And that makes sense, because you take a number and add 5 to it, you get the bigger number, right? Whenever you add 5 to something, it becomes bigger. So B will always be bigger. Now you're like, duh. But here's the thing. I'm going to ask you questions like this. And I've done it before in past math class where I have like quizzes and stuff, like which number's bigger and all that stuff, you know, what else do you know? And you need to know this. And they have no idea how to figure that out. Because they're too busy used to, all I know is how to move things around. I don't know what it's telling me. I just move it around. Why are you moving it around? Well, because I needed to get it to look like this, because that's what they told me to. Well, why is that useful? We're going to be talking about that in the next couple days. A is always smaller than B here. Question. How do we take this? Remember, this is our... If you take a number line and put all the answers, possible answers, right? 5 and 10, 2 and 7, 3 and 8. This is what your number line would look like. Is that very useful? No. What am I even looking at here? In fact, this looks like any problem. Give me all the numbers that are separated by 3. Color in the whole line, right? It doesn't really tell us anything. So we invented a way to make it a little more useful. This thing. Bum, bum, bum. Wait, I have that sound effect. Okay. You guys know what this is? It is the Cartesian coordinate plane. Not that kind of plane. This kind of plane. Cartesian because it was invented by a Frenchman named René Descartes. You ever heard of Descartes? The philosopher. He's kind of like Leonardo da Vinci, did a little bit of everything, right? And he said the philosophical statement of, I think, therefore I am. Basically, the philosophers around his time were like, do we really exist? Oh my God, what if we're a simulation? What if we're all just in a computer? And he's like, look, I can't prove that we exist, but I don't care whether we do or we not. You know why? Because I think. And since I'm thinking, I'm going to think about something else. I think, therefore I exist. He also invented this. All right, so instead of using A and B, he decided to use X and Y because they're not letters that are used a lot. Like imagine you're writing a book about math, right? You wouldn't want to use A and B because you never know if he's talking about A as in like a dog, a cat walked into a bar, right? Or are you talking about math? A times B, AB. We talking about these guys? We talking about A times B? I don't know, right? So we used X and Y because they're not used a lot. He said X is the horizontal stuff and Y is going to be the vertical, and that's going to allow us to look at what the solutions are, right? Here, if I just use one line, give me all the numbers that are separated by 5, right? Not very useful. On here, we can show all the numbers that are separated by 5. You said 5 and 10, right? So he said, here's 1, 2, 3, 4, 5. It's our number line, right? 0, 1, 2, 3, 4, 5, all the way off, right? It's the same thing as this. Here's 5 for one number. And here's 10. 1, 2, 3, 4, 5. Did I make it big enough? 6, 7, 8, 9. Oh, yeah. 5 and 10. There's that point we were talking about earlier. 5 goes with 10. If X is 5, Y has to be 10. If A is 5, B has to be 10, right? But that's not the only possible solution. You said 2 and 7, right? 2 and 1, 2, 3, 4, 5, 6, 7 also works. Okay? Do you see how we have infinite possibility here? I could put a point anywhere, couldn't I? But as soon as you tell me the rules, they're only separated by 5, right? Now it's not infinite. It's kind of less infinite. But wait a minute. Can you give me all the answers that are separated by 5? All the numbers that are separated by 5? Can you? No, why? There's infinitely many, right? But wait a minute. What about 3 and 3? Are they separated by 5? 3 and 3? Jordan's like, carry the 5, back to 7. No, they're not. So wait a minute. You're telling me there's infinitely many answers, but some answers are wrong? How can infinitely many things be right? Yet some answers don't count. Imagine an infinitely large dartboard. Okay? You got that in your brain? Infinitely large dartboard. And you take the dart and you throw it and you miss. You're like, I would do that. How can it be infinitely big and you miss? Here's our infinitely large dartboard.
No, throw it in.
That's one way. Here's our infinitely large dartboard. There are infinite set of numbers that are separated by 5, right? 5 and 10, 6 and 11. Any of those are good. You have infinitely many spots that you could hit, right? And they'd work. But there are also infinitely many spots that don't work. Like missing that dartboard. You see what I'm saying? Infinity is weird. Some infinities are bigger than others. All the numbers, that's a bigger infinity than all the numbers that are separated by 5, even though every number has a partner that's separated by 5. You see how every number appears? Right? All the numbers are separated by 5. Do all the numbers show up? Yeah, they do. But it's a smaller infinity than just all the numbers to begin with. Very bizarre. Very bizarre. What other numbers are separated by 5? How about 0 and 5? 1, 2, 3, 4, 5, right? What about 1 and 6? What about 3 and 8? What about 9 and... I'm sorry, 4 and 9. Are you noticing a pattern? Are you starting to see it? What about -1? Ooh, negative numbers. -1 and 4 are separated by 5. -2 and 3. I bet I can fill out the rest of these without having to even think. You see the pattern? This is all the numbers that are separated by 5. This is b minus a, or y minus x equals 5. This is all the numbers separated by 5. That's what this represents. Now, question. What kind of numbers am I missing here? I did 1 and 6, 2 and 7. What kind of numbers am I missing? Nope, got him. -1 and 4. Nice try. Negative. What's a negative? Oh, are you talking about like coordinate-wise? I've got -6 and I'm sorry, yeah, -6 and -1. They're separated by 5. I've got that. That's here. Good idea. We've got negative, positive, and we don't have positive, negative. I like what you're thinking. That's not what I'm asking, but that was good. What numbers are missing here, right? This is kind of like our number line. Remember, we had infinitely many. So much that we had to color in the whole number line, right? 2 and 7 work, 5 and 10 work. Here's our line, but just kind of turned. And this tells us, same line, but now it's useful because we know what isn't on the line, right? That's why this is useful. It's every possible number, but only the ones that are in combination like this. But what numbers am I missing? I did 1 and 6, 5 and 10. What kind of numbers am I missing here? -1 and 4, 0 and 5. Come on. What are your least favorite numbers? What kind of numbers didn't show up here? 1 and 6, 2 and 7. Ooh, we got them. Eventually, right? We've got 5 and 10. I could keep going. Now, what is a half plus 5, right? And again, when we ask what's a half plus 5, what we're asking is, if I take that first number I give you and add 5, I'm asking what's the other number. Remember, these are the same, right? This is how I can find two numbers that are 5 apart, right? 5 and 10 would be, because if I add 5, I get 10, right? A half and what? Yeah, she mentioned that. You just can't hear her because I turned down the mics. A half and what number separated by 5? That's what, when I ask that question, I'm asking this one. An easier question is, what's a half plus 5? 5.5, right? 5.5. So a half is like right here, and 5.5 is like here. Right? And it's on my line. What if I started filling in all of these? What's going to happen? Eventually, when I fill in a third, a quarter, all those plus 5, I'm going to get a solid line like I had before, right? Ladies and gentlemen, this is what algebra is all about, is finding relationships between A's and B's, X's and Y's, and showing that even though there's infinitely many solutions, it's only these ones that work. Anything over here won't be. It makes sense of the infinite. Why are we allowed to move stuff around? Because they're saying the same thing. It's just a different way of asking it. What numbers are separated by 5? This is telling you, give me a number and I can tell you the number that's separated by 5, right? It gives you answers to this. I want you guys to walk out of here. We'll come back tomorrow and talk about this some more, okay? Thanks for sticking around. Thanks for the inspiration on the Rubik's Cube today, Kaylee. I'll see y'all later, okay? Bye.